Let the modern world fade away. Take a deep breath, slow and easy, and for a moment, allow the weight of your day, the soft hum of your room, the small steady glow of your screen, the long list of things you carried through the hours to slip quietly into the background until there is only darkness and the gentle rhythm of your own breathing. Now imagine a different breath. 125 million years ago, on a soft, cool morning at the edge of a lake, in what will one day be called the Yixian Formation of northeastern China, a small dinosaur is running through the low mist that hangs over the shoreline. The sun is just rising. The eastern sky is a deep pale peach. The lake surface is still. The morning is deeply quiet, with only the smallest sounds of insects and small creatures moving. The small dinosaur is Sinosauropteryx prima. She's perhaps 3 feet long from snout to tail tip, weighing about 2 pounds. She is a small compsognathed theropod, one of the fast little predators that hunt insects and small lizards through the Yixian forest. Her body is covered in soft primitive feathers, more like fine down than the flight feathers of modern birds, but unambiguously feathers, and her feathers, as she moves through the mist, are specifically coloured in ways that we now know with substantial confidence. Her back is a warm reddish orange. Her belly is a pale, creamy white. Her tail is banded in alternating bands of ginger orange and pale cream, 6 or 7 distinct bands running from her hips to the tip of her tail. When she turns in the morning light, the countershading of her body creates a subtle 3-dimensional patterning that makes her hard to see against the dappled forest floor. When she moves quickly, the banded tail creates a slight flickering visual effect that may confuse predators trying to track her exact position. She is one of the most beautifully coloured small dinosaurs the fossil record has preserved for our modern reconstruction. Her specific pattern is now widely known in the modern paleontological community. Her specific individual body has become one of the most famous and most influential dinosaur specimens in the history of the field. She does not know she is beautiful. She does not know that in the year 2010, a research team led by Jacob Winther at the University of Bristol and Michael Benton at the same institution will publish the first detailed reconstruction of her exact colour pattern, based on the microscopic preservation of pigment-bearing structures called melanosomes in her fossilised feathers. She does not know that her ginger and cream tail will become one of the most famous examples of dinosaur colour reconstruction in the entire modern paleontological literature. She does not know that her patterned body will help launch one of the most active and rapidly developing areas of dinosaur research in the entire 21st century. She knows only her mourning, her hunt, her small, careful life in the Yixian forest. The specific individual moment we're watching, 125 million years ago in what will one day be northeastern China, is one specific individual life on one specific individual morning. She's not thinking about her species or her ecosystem or her paleontological significance. She's simply hunting. The specific colours on her body are hers to wear in the specific ecological context of her specific individual life. There is something beautiful about this specific mode of being. She has no worries about how her species will be classified. She has no concerns about how her specific colours will be interpreted. She is not thinking about how her body will fossilise. She's entirely focused on the immediate present of her hunt. Modern animals live in similar simple presence. A modern bird hunting insects in a modern morning is not thinking about her evolutionary lineage or the colour mechanisms that shape her plumage. She's entirely focused on catching the specific next insect. This simple presence in the immediate moment is one of the deep features of vertebrate consciousness. Tonight, we're going to walk slowly through what we now understand about dinosaur colour. We are about to honour Sinosauropteryx, and the small handful of other dinosaur species whose specific colours have been reconstructed from preserved melanosome evidence. We're going to walk through the science of melanosome preservation, the specific analytical techniques that make colour reconstruction possible, the specific research teams who have developed these techniques across the past 15 years. We will think about what the colours mean ecologically, countershading for camouflage, display patterns for social communication, iridescence for species recognition. We are going to acknowledge the substantial limits of what we can know. Many colours are not preservable in the fossil record, and the great majority of dinosaur species will never have their colour patterns reconstructed. We are going to walk through all of it slowly, in the soft theatre of your closed eyes, until the modern world falls completely away and the softly coloured dinosaurs of the deep past come into view. Before we step into any single Cretaceous scene, a small, honest framing. Dinosaur colour reconstruction, as we understand it tonight, is one of the most exciting and one of the most limited areas of modern paleontology. The exciting part is that we can, for a small number of exceptionally preserved specimens, reconstruct actual colour patterns with substantial confidence. The limited part is that this small number is very small. Only a handful of dinosaur species have preserved melanosome evidence sufficient for colour reconstruction. The vast majority of dinosaur species will never have their colours reconstructed, because their fossil preservation does not include the microscopic pigment-bearing structures needed for the analysis. We will walk through what we can honestly know, while remaining humble about what we cannot know. Some of the colour reconstructions we will discuss tonight are firmly supported by preserved melanosome evidence. Others are informed inferences based on comparison with modern animals of similar ecology. Still others are honest imagination anchored in what we can reasonably guess about dinosaur colour, based on general principles of animal colour evolution. We will try to be clear about which is which as we walk. This is a long walk. The question of dinosaur colour has been an active area of research since roughly 2008, when the first melanosome preservation was demonstrated in fossil feathers. Across the 17 years since then, the field has expanded rapidly, with new specimens analysed, new techniques developed, new interpretations published. We are in some sense walking through a research area that is still in its early stages, with much more to be discovered in the coming decades. So let the modern world fade away. Settle into whatever supports you. Breathe out slowly. Let the day go. There is no urgency tonight. Sinosauropteryx is running through the morning mist. The Ixian dawn is soft and cool. The walk is at the pace of slow, patient morning light, gradually revealing the colours of a Cretaceous world. If your eyes close along the way, that is perfectly all right. The colours will still be here, breathing in long, slow waves when you return. The whole subject of dinosaur colour is one of the most emotionally resonant areas of modern paleontology. It touches on the specific visible surface of the deep past, on how animals actually appeared to each other, on what the visual world of an ecosystem looked like when it was functioning. It connects the technical work of laboratory melanosome analysis to the immediate sensory experience of seeing an animal in her specific colours. It bridges the gap between paleontology as a specialised scientific field and paleontology as a general subject of human curiosity. There is something particularly satisfying about walking through this material at the pace this channel prefers. The specific reconstructions deserve careful attention. Each one is a small research achievement worth honouring in detail. The specific analytical techniques deserve careful explanation. The specific limits deserve honest acknowledgement. All of it deserves the slow, patient walking pace that a sleep documentary can offer. The dinosaur colour story is also, in some quiet sense, a story about the specific relationship between science and imagination. Older paleontology imagined dinosaur colours because it had no direct evidence. Modern paleontology partially reconstructs dinosaur colours from specific evidence. The relationship between what we imagine and what we can actually reconstruct is complex and evolving. As more evidence accumulates, the relationship shifts. What was previously guesswork becomes evidence-based. What remains guesswork is at least identified as such rather than presented with false confidence. This is one of the ways that scientific understanding matures across time, not by suddenly knowing everything, but by gradually replacing guesswork with evidence, one specific reconstruction at a time. The dinosaur colour story is a good example of this gradual maturation. We are grateful to have the time to walk through it properly. We begin with the science of it all, the specific analytical foundation on which every subsequent colour reconstruction rests. For most of the history of dinosaur paleontology, the question of what colour dinosaurs were was considered fundamentally unanswerable. Fossil bones do not preserve colour. The pigments that make modern animals brightly coloured decompose within days or weeks of death, long before any fossilization process can preserve them. The traditional consensus was that we could never know what specific colours any specific dinosaur wore. Museum paintings and popular illustrations depicted dinosaurs in grey, brown and dark green, on the assumption that these were the most likely colours for large reptiles, based on comparison with modern lizards and crocodiles. But the assumption was speculation. The actual colours of specific dinosaur species were unknowable. Then, in the early 2010s, that changed. The change came from the analysis of melanosomes. We're going to walk slowly through the specific technical steps involved in melanosome analysis. The technique is more elaborate than a casual description might suggest, and understanding the specific procedures helps us appreciate both the achievement of the technique and the specific limits of what it can and cannot determine. The analysis begins with the selection of an appropriate specimen. Not every dinosaur fossil is a candidate for melanosome analysis. The specimen must preserve enough soft tissue to potentially contain melanosome structures. Feathered specimens with visible feather impressions are the most common candidates. Specimens with preserved skin fragments are also candidates. Specimens with only bone preservation are not candidates, because melanosomes do not preserve in bone tissue. The specimen must also come from an appropriate depositional environment. Fine-grained matrices that resist chemical degradation are ideal. Coarse-grained matrices or matrices with significant chemical alteration are less suitable. The specific taphonomic history of the specimen matters substantially. Once an appropriate specimen has been identified, the actual analytical procedure begins. Small samples of the preserved tissue are removed for microscopic examination. The sampling is destructive of the specific material sampled, so paleontologists take samples carefully from locations that will not damage the overall specimen appearance or interpretation. The samples are prepared for electron microscopy. The preparation typically involves cleaning the samples to remove surface contamination, mounting them on specialized microscope stubs, and coating them with a thin layer of conductive material like gold or carbon to enable electron microscope imaging. The prepared samples are then examined under scanning electron microscopy at high magnifications. The microscope produces detailed images of the microscopic surface texture of the samples. In samples that preserve melanosome evidence, the microscope images show microscopic structures with specific shapes and sizes that correspond to the melanosomes. The specific shapes and sizes must be measured carefully. Eumelanosomes are typically elongated, roughly sausage-shaped, measuring approximately 1 to 2 micrometers in length. Pheomelanosomes are typically more spherical, measuring approximately 0.5 to 1 micrometer in diameter. The specific measurements are compared to reference measurements from modern bird feathers and modern reptile skin to confirm the identification. Once melanosomes have been identified, the specific arrangements and densities must be analysed. Different regions of a feather or skin sample show different melanosome patterns. Some regions have dense melanosome concentrations. Other regions have sparse melanosome distributions. Still other regions show no melanosomes at all. The specific patterns of melanosome distribution correspond to specific colour patterns in the original tissue. Dense eumelanosome concentrations produce black or dark brown coloration. Dense pheomelanosome concentrations produce reddish or reddish-brown coloration. Absence of melanosomes produces pale coloration. Mixed distributions produce intermediate colors. The analytical work involves careful documentation of the specific melanosome distributions across the specimen. Multiple samples from different body regions are examined. The specific patterns from each region are documented. The overall color pattern of the original animal is then reconstructed from the combined region analyses. Hold the moment lightly. The technique is more elaborate than it might sound in general description. Each specimen requires many months of careful laboratory work. Each analysis produces detailed documentation of specific melanosome distributions. Each color reconstruction is the product of substantial investment of expert time and specialized equipment. The reconstructions are also subject to specific limits. The technique reliably identifies eumelanin-based and pheomelanin-based coloration. It does not identify carotenoid-based coloration, structural coloration, that does not involve melanosomes or various other color mechanisms. The technique also does not always work perfectly. Some specimens that appear promising turn out, on detailed analysis, to have melanosome preservation that is too degraded for reliable color reconstruction. Some analyses produce results that are ambiguous or difficult to interpret. Not every attempt at color reconstruction produces a clear result. But when the technique does work, it produces genuinely reliable evidence about specific dinosaur color patterns. The Sinosauropteryx ginger and cream tail is not artistic imagination. It is based on specific melanosome evidence carefully analyzed and documented. The Anchiornis rusty crest and pied wings are similarly evidence-based. The Microraptor iridescent black is similarly evidence-based. The Borealopelta countershading, the Psittacosaurus flank patterns, the Diplodocus speckled skin, all of these are based on real analytical evidence rather than artistic speculation. We honor the technique for what it can achieve. We remain humble about what it cannot achieve. We continue to walk through the specific reconstructions it has enabled. We move on. Melanosomes are microscopic pigment-bearing structures found in the cells of most modern vertebrates. They are the source of the black, brown and reddish colors in mammalian skin and hair, in bird feathers, in reptile scales, in amphibian skin. Different types of melanosomes produce different colors. Eumelaноsomes, which are roughly sausage-shaped, produce black or dark brown colors. Pheomelaноsomes, which are more spherical, produce reddish or reddish-brown colors. The specific arrangement and density of melanosomes in a tissue determines the specific shade and pattern of coloration in that tissue. Critically for paleontology, melanosomes are made of resistant organic materials that can, under exceptional preservation conditions, persist for tens of millions of years in fossil form. When a fossil feather or fossil skin sample is preserved in a fine-grained matrix that resists chemical degradation, the melanosomes in the original tissue can survive as microscopic structures embedded in the fossil. If paleontologists can identify these preserved melanosomes in a fossil specimen, and if they can determine the specific types and arrangements of the melanosomes, then they can reconstruct the original color pattern of the tissue with substantial confidence. The recognition that melanosomes could be preserved in fossil feathers came in the middle 2000s, from analyses of fossil bird feathers from various deposits. The extension to non-avian dinosaur feathers came shortly after, as researchers examined the feathered small theropod specimens from the Ixian Formation and other Chinese Cretaceous deposits. By the late 2000s, it was clear that many exceptionally preserved dinosaur specimens contained melanosome evidence that could be analyzed to reconstruct original color patterns. The first detailed dinosaur color reconstruction was published in 2010 by the research team led by Jakob Winter, then a graduate student at Yale University and now a paleontologist at the University of Bristol. Winter and his collaborators analyzed the melanosome evidence preserved in the feathers of Sinosauropteryx prima. Their analysis identified the specific types and arrangements of melanosomes in different regions of her body and reconstructed the specific color pattern that these melanosomes originally produced. Their reconstruction was the ginger and cream pattern we have already met. Her back was a reddish-orange, produced by densely packed pheomelanosomes. Her belly was pale, produced by the near absence of melanosomes. Her tail was banded, with the bands alternating between pheomelanosome-rich regions, reddish-orange, and melanosome-poor regions, pale. The overall pattern was a countershaded body with a distinctive banded tail. The paper was published in the journal Nature. It was one of the most impactful paleontological papers of the entire 2010s. It demonstrated for the first time that specific dinosaur colour patterns could be reconstructed from fossil evidence. We are set to pause and honour the human researchers who developed the melanosome analysis technique. The specific individuals who did this work deserve their own quiet recognition, because the field of dinosaur colour reconstruction essentially did not exist before their innovations. The central figure in the development of the technique is Jakob Winther. Winther is a paleontologist currently based at the University of Bristol in the United Kingdom. He was born in Denmark and did his graduate training at Yale University in the middle 2000s, where he began the work that would eventually establish the modern subfield of dinosaur colour reconstruction. His initial insight came from careful examination of fossil bird feathers under high magnification electron microscopy. He noticed that some fossil feathers contained microscopic structures that appeared to be preserved cellular organelles. Comparing these structures to reference samples of modern bird feathers, he identified the microscopic structures as preserved melanosomes. This identification was not immediately obvious. Previous researchers who had examined fossil feathers had noticed the microscopic structures but had interpreted them as fossilized bacteria rather than as preserved cellular organelles. The bacterial interpretation had been the mainstream view for decades. Winther's insight was to recognize that the specific shape, size, and arrangement of the structures were consistent with melanosomes but not with bacteria. He published his initial identification in 2008 in the journal Biology Letters. The paper argued that the microscopic structures in fossil bird feathers were preserved melanosomes, not fossilized bacteria. The paper was received with substantial skepticism by the paleontological community, but the specific evidence Winther presented was convincing to enough researchers that the interpretation gained traction. Over the following 2 years, Winther and his collaborators extended the interpretation from fossil bird feathers to fossil dinosaur feathers. They analysed melanosome evidence in the Yixian small-feathered theropod specimens. They demonstrated that the same specific microscopic structures were present in dinosaur feathers as in bird feathers, and that the melanosome interpretation was consistent across both fossil groups. The 2010 Sinosauropteryx colour reconstruction was the culmination of this initial work. The paper, published in Nature with collaborators including Michael Benton at Bristol, established that dinosaur colour reconstruction was possible. The paper generated substantial media attention and inspired numerous follow-up studies. Over the following 15 years, Winther has continued to lead the field. He has published multiple additional colour reconstructions, including the Psittacosaurus work we honoured earlier. He has developed increasingly sophisticated analytical techniques for melanosome identification. He has trained multiple graduate students who have gone on to establish their own research programs in dinosaur colour reconstruction. He has become, in some quiet sense, the founding figure of the modern subfield. His collaborators have contributed substantially. Michael Benton at Bristol is one of the most respected dinosaur paleontologists in the world, and his collaboration with Winther has helped legitimize the melanosome work within the wider paleontological community. Ryan Carney at Brown University has led important work on Anchiornis and other early feathered dinosaurs. Quangguo Li at Peking University has led important work on the Chinese Cretaceous specimens. Fian Smithwick and other researchers at Bristol have continued the work at Bristol as the field has expanded. Multiple other research teams around the world have also contributed. Researchers at the Field Museum in Chicago have analysed colour evidence in various specimens. Researchers at the Royal Tyrrell Museum in Alberta have led the Borealopelta work. Researchers at various Chinese institutions have led the work on Yixian and other Chinese Cretaceous specimens. The field is now a substantial international research community. Multiple universities and museums have specialists working on dinosaur color reconstruction. Multiple laboratory facilities have the specialized electron microscopy equipment needed for the melanosome analysis. Multiple graduate students are being trained in the specific techniques required for the work. Let your breath slow. The development of the field is one of the most encouraging stories in modern paleontology. A single insight by a single graduate student in the middle 2000s has led, across the following 15 years, to a substantial international research community and to a fundamental transformation of our understanding of what dinosaurs looked like. There is something profoundly satisfying about this. Individual researchers can, through careful observation and creative interpretation, open up entirely new avenues of scientific inquiry. Vinther saw something in the fossil evidence that other researchers had missed. He argued for his interpretation against initial skepticism. He accumulated the additional evidence needed to convince the wider community. He built the institutional infrastructure needed to sustain the work across multiple decades. The wider community accepted his interpretation and joined the research effort. New researchers were trained. New techniques were developed. New specimens were analyzed. New color reconstructions were published. The field expanded from a single paper in 2008 to a substantial subfield by 2026. This is how paleontology grows. Individual insights combine with institutional support to produce collective advances. The Nanotyrannus story we honored in another episode showed one version of how this works, with individual researchers arguing across decades until evidence accumulated to resolve a specific question. The dinosaur color story shows a different version, with a single insight opening up an entirely new research area that has expanded rapidly across the following 15 years. Both patterns are legitimate. Both patterns produce important advances in scientific understanding. Both patterns depend on individual researchers who are willing to look at the fossil evidence with fresh eyes and to argue for interpretations that older paleontology missed or dismissed. We're going to walk to a broader view of the colored dinosaur ecosystem. Individual color reconstructions tell us about specific species, but the wider question is what the whole visual world of a dinosaur ecosystem actually looked like when all species were participating together. We are about to imagine, gently and honestly, what the visual environment of a specific dinosaur ecosystem probably looked like at a specific moment in the deep past. We will hold the imagination lightly. Most of what we're about to describe is honest inference rather than direct evidence. We are going to visit the Hell Creek Formation in the last million years of the Cretaceous. This is one of the most famous dinosaur ecosystems in the entire world, familiar from many other episodes of this channel. Tyrannosaurus rex hunts across the floodplain. Triceratops herds graze at the riverbanks. Edmontosaurus hadrosaurs move through the marshes. Ankylosaurs patrol the drier ground. Dromaeosaurs and troodontids fill the smaller predator niches. Pterosaurs glide overhead. Small mammals hunt in the leaf litter. We do not have preserved melanosome evidence for most of these species. Their specific colors are inference rather than direct reconstruction. But we can use the general principles we have walked through tonight to make reasonable guesses about what the Hell Creek visual environment probably looked like. Tyrannosaurus rex was almost certainly countershaded. His back was probably dark, either dark brown or dark grey, produced by dense eumelanosomes. His belly was probably pale, produced by absence of melanosomes. His body probably showed some pattern variation, possibly stripes or spots providing additional camouflage in his forest hunting habitats. His overall coloration was probably subtle rather than flashy, appropriate to an ambush predator who needed to avoid detection by his prey. Triceratops was probably countershaded and patterned. Her back was probably darker than her belly. Her flanks probably showed pattern variation. Her frill and horns may have been more brightly coloured, possibly serving display functions for social communication with other Triceratops during breeding season. Modern display features in horned mammals like modern deer antlers often show specific coloration that emphasises the display feature, and Triceratops' horns and frills may have followed similar patterns. Edmontosaurus was probably countershaded and probably showed pattern variation for individual recognition within her migratory herds. Modern large migratory mammals show similar patterns. Her overall coloration was probably subtle, adapted to her open plain habitat where camouflage against grass and low vegetation would be important. Ankylosaurus, being armoured and thus already substantially protected from predators, may have had less need for countershading than her ceratopsian and hadrosaur neighbours. But comparison with Borealopelta suggests that even armoured dinosaurs were countershaded, probably reflecting the general vertebrate pattern that countershading provides some additional protection even when other defences are also present. The dromaeosaurs and troodontids were probably countershaded and probably showed complex colour patterns similar to modern hawks or owls. Their overall coloration was probably adapted to forest hunting environments where broken patterns of light and shadow provide the primary background for their camouflage. The pterosaurs were probably coloured in ways adapted to aerial life. Modern soaring birds like eagles and vultures show specific colour patterns that make them visible against the sky from below, helping their species mates locate them, while remaining relatively cryptic against the ground from above. Pterosaurs probably followed similar patterns. Settle for a moment. Watch the Hell Creek ecosystem in your imagination. The visual environment is complex and varied. Every large animal is countershaded. Every animal shows some pattern variation. The overall visual palette is dominated by earth tones: browns, reds, greys, dark greens, tans, creams. Bright colours are probably rare and mostly restricted to display features on specific body regions of specific species. The whole ecosystem is beautiful in a subtle way. Not flashy, not spectacular, but beautifully adapted to the ecological realities of a working predator-prey ecosystem. Every colour pattern is doing specific functional work. Every species has evolved the specific visual appearance that its ecological role required. This is what the Hell Creek probably looked like. Not the uniform grey or greenish tones of older popular illustration, but a complex earth-toned world of counter-shaded animals with specific pattern variations serving specific functions. The whole visual world of the Mesozoic was probably like this. Every dinosaur ecosystem, across every period from the Triassic through the end of the Cretaceous, was probably filled with counter-shaded, pattern-varied animals. The specific patterns varied by species and by ecosystem, but the underlying visual grammar was consistent. Bright colours were probably restricted to display features. Iridescence was probably restricted to specific Pravian lineages. Overall body coloration was probably subtle and adapted to camouflage in specific habitats. This general picture is probably accurate for the vast majority of dinosaur species across the vast majority of dinosaur time. Breathe slow. This is a slightly different picture than the spectacular bright dinosaurs of some modern popular illustration. The reality was probably more subtle, more adapted to ecological function, less spectacular than pop culture sometimes depicts. But it was still beautiful. It was still visually rich. It was still a world worth honouring for what it actually was. The specific difference between pop culture dinosaur coloration and the specific evidence-based reconstructions is worth spending a moment on. Modern movies, video games, and children's toys often depict dinosaurs in extremely bright colours. Bright greens, bright reds, bright blues, elaborate multicolour patterns. These specific artistic depictions are eye-catching and commercially successful, but they generally do not reflect the specific evidence we have from melanosome analysis. The specific pop culture colours are chosen for visual appeal and audience engagement. Children respond to bright colours. Adults engage more with visually striking imagery. product designers know that bright dinosaur toys sell better than muted dinosaur toys. Movie directors know that dramatic dinosaur close-ups need visual variety to hold audience attention. All of these commercial pressures push pop culture dinosaur depictions toward brighter, more elaborate colorations than the specific fossil evidence supports. The specific evidence-based reconstructions we have honored throughout tonight tell a different story. Real dinosaurs were, based on the specific melanosome analysis, mostly countershaded in earth tones. Bright colors were mostly restricted to specific display features on specific body regions. The overall visual environment was more muted than pop culture depictions suggest. This is not an argument against pop culture dinosaur imagery. Bright dinosaur toys have their own value in engaging children with paleontology. Dramatic movie dinosaurs have their own value in entertaining audiences. The specific pop culture tradition has helped generate substantial public interest in dinosaurs and paleontology. But we should be clear about the specific difference between evidence-based reconstruction and artistic interpretation. When you see a bright green Tyrannosaurus Rex in a movie, you are seeing an artistic interpretation, not a scientific reconstruction. When you see an evidence-based reconstruction of Sinosauropteryx with her specific ginger and cream body, you are seeing a specific pattern documented in specific fossil evidence. Both types of imagery have their place, but they represent different types of claims and should be recognized as such. We honor the Mesozoic as it probably actually looked, not as older illustration depicted it, not as pop culture sometimes exaggerates it, but as the specific color reconstruction suggests it probably was, a complex earth-toned world of countershaded, pattern-varied animals, each species adapted to her specific ecological role, all participating together in the visual environment of the great pre-extinction dinosaur communities. We move on. Winter is now, in 2026, in the middle of his career. He continues to lead the field. He continues to develop new techniques and analyze new specimens. His work will continue to shape our understanding of dinosaur color for at least the coming decade, and probably longer. His students will carry the field into the next generation. New graduate students who study with him now will be the senior researchers of the 2030s and 2040s. The specific techniques they develop, the specific specimens they analyze, the specific color reconstructions they publish will further expand our understanding beyond the current state. The field will continue. Each decade will bring new advances. Our picture of dinosaur color will become progressively more detailed and more nuanced. We honor Winther and his collaborators. We honor the field they have built. We honor the specific graduate students who will carry the work forward. We move on. It opened up an entirely new subfield of dinosaur paleontology. It transformed how paleontologists thought about the visible surface of dinosaurs. Take a deep breath. Let the significance settle. Before the Winther paper, dinosaur color was considered fundamentally unknowable. After the Winther paper, dinosaur color became a legitimate active research question with a specific analytical methodology and a growing body of reconstructed color patterns for specific species. The paper was one of the most important paradigm shifts in modern dinosaur paleontology. We are going to walk through several of the other specific dinosaur species whose colors have been reconstructed. We are about to walk through the ecological interpretations of the reconstructed colors. We are going to walk through the important limits on what we can and cannot know. But first, we should honor Sinosauropteryx herself, running through her Yixian morning, wearing the specific colors that human science eventually reconstructed from her preserved melanosomes. She does not know she's being watched. She continues her morning hunt through the mist. Her ginger back catches the first warm light of the dawn. Her banded tail moves gently behind her as she runs. Her small feathered body is a moving pattern of orange and cream against the darker greens and browns of the Yixian forest floor. We watch her for a long, quiet moment. She's one of the most fully known small dinosaurs in the entire fossil record. We know her anatomy in detail from multiple well-preserved specimens. We know her ecological niche as a small, fast insectivore and small vertebrate predator of the Yixian forest floor. We know her general behavior from comparison with modern small theropod-like animals, and now, uniquely, we know her actual colors. She is beautiful. She was beautiful when she lived. She would have been noticed by the other animals of her ecosystem, seen against the forest floor and the streambed edges where she hunted, remembered by her fellow Sinosauropteryx as an individual with her own specific pattern of banding and countershading. Her colors served specific ecological functions. The countershaded back and belly pattern helped hide her from aerial predators looking down at her against the dappled forest floor. The banded tail may have served as a display element for social communication with other Sinosauropteryx, and may also have helped confuse pursuing predators by breaking up the outline of her body during high-speed movement. The specific reddish-orange tone of her back may have provided additional camouflage against the fallen conifer needles and dry ferns of the Yixian forest floor. Every element of her color pattern probably had a specific adaptive function. Her colors were not arbitrary. They were the product of millions of years of natural selection shaping her species towards specific ecological roles. She continues her morning hunt. The mist begins to lift as the sun rises higher. The Yixian forest brightens. She catches a small insect, swallows it, continues her patrol. Her banded tail flickers behind her as she runs. We move on. We will walk to another Yixian formation species whose colors have been reconstructed with substantial confidence. She is Anchiornis huxleyi, the four-winged theropod who is one of the most extraordinary small-feathered dinosaurs in the entire fossil record. Anchiornis is slightly older than Sinosauropteryx, dating from around 160 million years ago in the late Jurassic Teotihuacan Formation of northeastern China. She's a small Paravian theropod, closely related to the truebird lineage but not yet a truebird herself. She's perhaps 14 inches long from snout to tail tip, weighing about 1/4 pound. Her body is covered in long, complex feathers, with feathered wings on both her forelimbs and her hind limbs, giving her the distinctive four-winged body plan that characterizes this small theropod group. Her colors have been reconstructed by multiple research teams, including work by Guangguo Li and colleagues at Peking University, published in Science in 2010. The reconstructed color pattern is remarkable. Her body was primarily grey, with contrasting patches of white and rust on the wings and legs. Her head bore a distinctive rusty crest of feathers, similar to the coxcomb of a modern rooster. Her wing feathers were black with white patches, creating a pied appearance. Her leg feathers matched her wing feathers in the same black with white pattern. Let the moment open. Watch her in your imagination. She's standing on a low branch of a Jurassic conifer, her small feathered body illuminated by the morning sun, her grey body, her rusty crest, her black and white wing and leg feathers. She looks, in some deep evolutionary sense, like a small colourful bird, even though she is not yet quite a bird. The colour pattern of Anchiornis has become one of the most famous dinosaur colour reconstructions. Her rooster-like crest and her pied wing feathers make her instantly recognisable in modern paleontological illustration. She is one of the most commonly depicted small dinosaurs in modern children's dinosaur books and popular science media. Her colours served specific functions. The grey body provided general camouflage in the dappled forest environment. The rusty crest was almost certainly a display feature, used in social communication with other Anchiornis, particularly during mating displays. The black and white wing pattern may have served species recognition functions, helping Anchiornis distinguish members of her own species from similar-sized theropods. She's one of the most fully known small-feathered dinosaurs in the entire fossil record. Her preserved specimens are exceptionally complete. Her anatomy is well documented. Her feather structure is remarkably preserved. Her colours are reconstructed with substantial confidence. She is, in some quiet way, the small feathered dinosaur we know most fully. We watch her for a long, quiet moment. She stands on her branch, alert to the morning activity of the forest around her. Her small crest catches the morning light. Her pied wing feathers flutter slightly in the gentle breeze. She is beautiful. She was beautiful when she lived. Her fellow Anchiornis would have recognized her by her specific individual variation in the general species color pattern. She launches into flight. Her four wings work together in the slightly awkward but functional flight of an early Paravian. She flies from her branch to another branch across a small clearing. She lands, folds her wings, resumes her watch of the forest. We're going to walk to another small feathered theropod whose colours have been reconstructed with substantial confidence. She is Microraptor guy, the small four-winged dromaeosaur of the early Cretaceous Yixian formation. Microraptor is one of the most extraordinary small dinosaurs ever discovered. She is a true dromaeosaur, a member of the raptor family that produced Velociraptor and Deinonychus. But she's much smaller than those famous relatives. She reaches lengths of only 24 inches from snout to tail tip, weighing about 2 pounds. She's the size of a modern crow. Her most distinctive feature is her four wings. She has feathered wings on both her forelimbs and her hind limbs, similar to the four-wing configuration of Anchiornis, but with the wings even more developed for functional flight. Her hind limb wings are large and asymmetrical, with the feathers arranged in a way that generates aerodynamic lift when she glides. She was almost certainly capable of powered flight, or at least of active gliding between trees, using her four wings together in coordinated aerodynamic action. Her colours have been reconstructed by multiple research teams, most notably by Guangguo Li and his colleagues at the Beijing Museum of Natural History, working with international collaborators including Ryan Carney at Brown University. Their analysis, published in Science in 2012, identified the specific melanosome types and arrangements throughout her body. Her feathers were, throughout her body, primarily black, but not a plain matte black. The specific arrangement of the melanosome in her feathers produced structural iridescence, similar to the iridescent black feathers of modern crows and ravens. When light struck her feathers at specific angles, the feathers reflected the light in ways that produced blue, green, and violet iridescent flashes across the primarily black surface. She was iridescent. Her body shifted colours depending on the angle of the light and the angle of the viewer. In some views, she was pure black. In other views, she flashed with blue-green iridescence. In still other views, she showed violet highlights. This was the first documentation of iridescent colour in any non-avian dinosaur. We are set to walk to one more early bird whose colours have been reconstructed. She is Confuciusornis sanctus, the small early bird from the Yixian formation, one of the most abundant fossil birds in the entire early Cretaceous of China. Confuciusornis lived approximately 125 million years ago in the same Yixian ecosystems as Sinosauropteryx, Microraptor, Psittacosaurus, and the various small feathered dinosaurs we've been honouring tonight. She's a small crow-sized bird, about the size of a modern jackdaw, with a body length of approximately 18 inches and a wingspan of approximately 2 feet. She's one of the most abundant fossil bird species ever discovered. Multiple hundreds of Confuciusornis specimens have been recovered from the Yixian formation, ranging from complete articulated skeletons to fragments and isolated bones. The species is so abundant that Confuciusornis specimens have become almost routine in Chinese paleontological collections, though the best preserved examples remain scientifically significant. Her body plan is transitional between the small, feathered non-avian theropods and true modern birds. She has a toothless beak, one of the earliest examples of tooth loss in the bird lineage. She has fused pagostyle vertebrae at the base of her tail, another advanced avian feature. But she retains claws on her wings, an ancient feature that most modern birds have lost, and her overall body proportions are more theropod-like than modern bird-like. Her colours have been reconstructed by multiple research teams working with the exceptionally preserved Yixian specimens. The specific reconstruction published across several papers from the middle 2010s onward, shows a distinctive pied plumage pattern. Her body was primarily dark, produced by dense melanosome concentrations. Her wing feathers showed patches of white and lighter coloration on a darker background. Her long tail streamers, which are distinctive features of male Confuciusornis specimens, were dark. Her body coloration also showed subtle countershading, with the belly slightly paler than the back. The overall visual effect was similar to some modern pied bird species. Modern magpies show similar black and white patterning, though the specific arrangement is different. Modern ravens with white wing patches show related patterns. The Confuciusornis pattern is distinctive but recognizable as part of the same general visual family that many modern birds inhabit. Soft and slow. Watch her in your imagination. She is flying from one Yixian conifer to another, her small dark body catching the morning light, her wings showing their pied pattern as she extends them for a glide. Her long tail streamers trail behind her. Her body is visible against the sky. She is beautiful. Her ancestors were the small feathered theropods we have been honouring. Her descendants are the modern birds you know in your own world. She is one small transitional form in the great evolutionary journey from dinosaur to bird, preserved for our modern examination with her specific colours intact. The specific colours serve specific functions. The overall dark body provided general camouflage. The pied wing pattern probably served species recognition and display functions. The long tail streamers in males were almost certainly a sexual display feature, used to attract females during mating displays. Modern birds with similar long tail streamers, like the modern lyrebirds or the modern paradise flycatchers, use their tail streamers in similar display functions. The specific evolutionary origin of tail streamer displays in bird lineage may go back at least to Confuciusornis, 125 million years before the modern birds who continue to use similar displays today. The evolutionary continuity is direct. The specific display coloration mechanisms that evolved in Confuciusornis have been preserved through the bird lineage across the intervening 125 million years. We are going to walk out of the small feathered theropods for a moment. So far we have honoured dinosaurs whose feathers preserve the melanosome evidence needed for colour reconstruction. But feathers are not the only tissue that can preserve melanosomes. Under exceptional preservation conditions, dinosaur skin itself can preserve enough microscopic detail to allow colour reconstruction of scaly and armoured dinosaurs. The most famous example is Borealopelta markmitchelli, the great armoured nodosaur of the early Cretaceous Clearwater Formation of Alberta, Canada. Borealopelta is one of the most exceptionally preserved dinosaur specimens ever discovered. She was excavated in 2011 from the Suncor oil sands mine near Fort McMurray, Alberta, by a mine equipment operator named Sean Funk. Funk was working a routine excavator shift when his equipment struck an unusually hard object in the tar sand. He stopped work and examined the object more carefully. It appeared to be a large fossil, with what looked like an intact body outline preserved in the tar sand matrix. The mine company contacted the Royal Tyrrell Museum in Drumheller, Alberta. A paleontological team led by museum paleontologist Caleb Brown was dispatched to examine the specimen. What they found was extraordinary. The specimen was a nearly complete nodosaur, preserved with substantial three-dimensional integrity, including preservation of the skin surface across much of her body. Her armoured back was fully articulated. Her tail was intact. Her legs were in their original life posture. Her head was preserved with the horny keratin sheaths still covering the bony osteoderms. Even the specific patterns of her armour arrangement were preserved in situ. The specimen represented a young adult female nodosaur who had died in the shallow sea that covered the Alberta region in the early Cretaceous, around 110 million years ago. Her body had sunk to the sea floor. She had been rapidly buried by fine mud, which had preserved her body in its original three-dimensional shape, rather than crushing it flat as most dinosaur fossils are crushed. over the following 110 million years, the mud had compressed into shale, but had preserved the fine surface details of her body throughout the compression process. The Royal Tyrol Museum team spent 6 years carefully excavating and preparing the specimen. When the preparation was complete, the results were unprecedented. The specimen was one of the most complete dinosaur skin preservations ever recovered. Every scale was visible. Every osteoderm was in place. The specific texture of the skin between the armor plates was documented, and the skin, examined for melanosome evidence, revealed her original color pattern. Brown and his colleagues, working with international specialists in melanosome analysis, identified the specific melanosome types and arrangements throughout her preserved skin. Their analysis, published in Current Biology in 2017, reconstructed her original color pattern with substantial confidence. Borealopelta was countershaded. Her back and upper flanks were dark reddish-brown, produced by dense melanosome concentrations. Her belly and lower flanks were pale, produced by the absence of melanosomes. Her overall body pattern showed the classic countershading that hides an animal from predators looking down from above by making her back match the darker forest floor, and hides her from predators looking up from below by making her belly match the brighter sky. Rest in this. The Borealopelta countershading is one of the most quietly important dinosaur color reconstructions in the entire fossil record. She was a large armored dinosaur, 20 feet long and weighing over 1 ton. She was covered in extensive bony armor plates. She had every physical defense a nodosaur could evolve, and she was still countershaded. The countershading tells us something important about her ecology. Even with all her armor, she was still vulnerable to predators. Something in her ecosystem could kill her if it got close enough. The countershading was an adaptation to help her avoid detection by predators who were looking down at her, most likely large theropod predators similar to the great tyrannosaurs and Confuciusornis of the Middle Cretaceous. Modern large armored mammals show similar countershading. Modern rhinoceros are countershaded despite their thick armor and formidable size. Modern elephants show subtle countershading despite their massive bulk. The pattern is widespread across large terrestrial vertebrates, because even the largest and most well-defended animals benefit from the modest additional predator avoidance advantage that countershading provides. Borealopelta shows that the same countershading pattern was present in dinosaurs, and specifically in armored dinosaurs. The predator avoidance pressure was strong enough to select for countershading, even in an animal that was already extensively armored. The specific color of her back, the reddish-brown produced by dense melanosomes, is also interesting. Modern animals that live in forest environments with substantial reddish-brown ground cover, fallen leaves, red earth soils, often evolve reddish-brown backs for camouflage. The Alberta Cretaceous forest floor was probably rich in fallen conifer needles and other reddish-brown organic material. Borealopelta's back color would have matched this background substantially, providing significant camouflage. She's now displayed at the Royal Tyrol Museum. Visitors to the museum can stand in front of her preserved body and see the actual dinosaur in her original 3-dimensional shape, with her original armor arrangement, in a museum display that is closer to seeing a living dinosaur than any other exhibit anywhere in the world. We are going to walk to another dinosaur whose skin has preserved enough melanosome evidence for color reconstruction. She is Psittacosaurus mongoliensis, the small early ceratopsian of the early Cretaceous Yixian Formation. Psittacosaurus is one of the most abundant dinosaurs in the early Cretaceous of Asia. She is small by ceratopsian standards, only about 6 feet long from snout to tail tip, weighing about 45 pounds. She's a bipedal browser, walking on her hind legs primarily but capable of dropping to all fours when browsing close to the ground. She has the characteristic ceratopsian parrot-like beak, but she does not yet have the elaborate frills or horns of the later great ceratopsians like Triceratops. She's important for our story because one specific Psittacosaurus specimen from the Yixian Formation preserves exceptional skin detail, including melanosome evidence that has been analysed for colour reconstruction. The specimen was described by Jakob Winter and his colleagues in Current Biology in 2016. The specimen preserves the animal's body outline in remarkable detail. The skin surface shows fine-scale texture. The specific arrangement of scales across different body regions is documented, and the melanosome analysis reveals the specific colour pattern of the animal. Psittacosaurus was countershaded. Her back and upper flanks were dark, produced by dense eumelanosome concentrations. Her belly and lower flanks were pale, produced by the absence of melanosomes. Her flanks showed a gradient between the dark back and pale belly. Her tail bristles, the strange pipe cleaner-like structures that projected from the top of her tail, were also dark. The general pattern is similar to what we have already seen in Borealopelta and in the small feathered theropods. Classic countershading serving predator avoidance functions. But Psittacosaurus adds some interesting specific details. Her back was not uniformly dark. Instead, the dark coloration formed a series of specific patterns, including what appears to be a pattern of stripes or spots across her back region. The specific pattern is difficult to reconstruct in full detail because the preservation is not perfect, but the analysis shows enough pattern variation across her back to indicate that she was not simply a uniform dark colour. Her flanks also show pattern variation. There are darker patches and lighter patches in specific arrangements that appear to be non-random. These may represent additional camouflage patterns, or they may represent species recognition markers that would have helped Psittacosaurus identify other members of her species. Her belly was pale, but not pure white. The pale coloration is consistent with the general countershading pattern, but the specific shade may have been a pale cream or pale beige rather than a pure white. Take a deep breath. The Psittacosaurus reconstruction is important because it demonstrates that non-avian dinosaurs used complex specific colour patterns rather than uniform simple colours. The countershading was accompanied by pattern variation. The animals had specific colour designs, not just general colour tones. The specific patterns had specific functions: countershading for predator avoidance, stripes, or spots for additional camouflage, species recognition markers for social identification. All of these functions are present in modern colour patterns of various vertebrate species, and all of them appear to have been present in Psittacosaurus as well. The evolutionary continuity from Psittacosaurus's colour patterns to modern reptile and bird colour patterns is meaningful. The same specific colour functions were shaping animal appearance 125 million years ago that shape animal appearance today. Vertebrate colour evolution is deeply continuous across the KPG boundary and across the intervening geological periods. Pause here. Watch Psittacosaurus in your imagination. She's standing at the edge of a small stream in the Yixian forest, drinking cautiously. Her body shows the countershading we have described: dark back, pale belly, gradient flanks. Her back shows the pattern variation, with darker and lighter patches. Her tail bristles project darkly from her back. Her small parrot-like face is dark on top and paler underneath. She drinks, looks up to check for predators, drinks again. She's alert but not anxious. Her camouflage is helping her hide from any potential predators, watching the stream from the surrounding forest. She finishes drinking and moves back into the forest. She walks in her characteristic bipedal with occasional drops to all fours gait. She disappears into the vegetation. We watch her go. The Yixian forest continues its morning activity around us. Somewhere in the deeper canopy, Sinosauropteryx is hunting insects. Somewhere higher, Anchiornis is perched on a branch watching the morning. Somewhere gliding between the trees, Microraptor is flashing his iridescent black wings. The whole Yixian ecosystem is a place of colour. Not just grey and brown dinosaurs, as older paleontology often depicted them, but specifically coloured dinosaurs, each with their own reconstructed colour pattern, each with their own ecological role, each participating in the visible surface of the Cretaceous world. We are set to walk to one of the most recent and most exciting dinosaur colour reconstructions. In late 2025, a research team published the first melanosome-based colour reconstruction of a sauropod dinosaur. The species was Diplodocus, the great long-necked sauropod of the late Jurassic Morrison Formation. The specific reconstruction has significant implications for our understanding of the great sauropods and their appearance. The specimen came from the Mother's Day quarry in Montana, one of the classic Morrison Formation localities. The quarry has produced numerous sauropod specimens across decades of paleontological work, including several Diplodocus individuals in various states of preservation. The specimen used for the colour reconstruction preserves fragments of skin from the animal's back and flanks. Skin preservation in sauropod specimens is relatively rare. Most sauropod fossils are known from bones only, with the surrounding skin having decomposed before fossilization. The Mother's Day quarry specimens are exceptional because the specific depositional environment preserved fragments of skin along with the bones. The skin fragments show the characteristic scale patterns of sauropod hide, along with sufficient microscopic preservation for melanosome analysis. The research team, led by paleontologists at multiple international institutions, analysed the melanosome evidence in the preserved skin fragments. Their analysis, published in December 2025, reconstructed the specific colour pattern of Diplodocus's back and flanks. The analysis showed that Diplodocus was not the uniformly grey sauropod of older popular reconstructions. Instead, she showed complex speckled and patterned coloration across her back and flanks. Specific regions of her body were dark, other regions were pale. The overall pattern was one of significant spatial variation in coloration, similar to the patterned skin of modern large reptiles like some giraffes and some large lizards. The specific dark coloration was produced by dense eumelanosome concentrations, giving the dark patches a black or dark brown appearance. The pale coloration was produced by the near absence of melanosomes, giving the pale patches a light grey or pale beige appearance. The specific arrangement of dark and pale patches formed a distinct pattern that varied across different regions of her body. Her back appears to have been generally darker than her flanks, with dark patches concentrated along the spine. Her flanks showed the specific speckled pattern, with darker and lighter patches interspersed in a non-random arrangement. Her belly, based on the countershading principle that appears widespread across dinosaurs, was probably pale. Let your shoulders drop. The Diplodocus reconstruction is important because it demonstrates that even the great sauropods, the largest land animals that have ever lived, had specific complex colour patterns rather than uniform simple colours. The traditional depiction of sauropods as uniformly grey or uniformly greenish is almost certainly wrong. Real sauropods were patterned. Real sauropods had specific colour designs. The specific functions of Diplodocus's patterned coloration are interpretive. The countershaded back and belly pattern probably served predator avoidance functions, similar to the countershading patterns we have seen in Borealopelta and Psittacosaurus. But sauropods, as adults, were largely immune to predator attack because of their sheer size. Adult Diplodocus were too large for even the great Morrison Formation theropods like Allosaurus to successfully attack, so the countershading pattern may reflect ancestral predator avoidance selection that persisted even though adult sauropods no longer needed it, or it may have provided predator avoidance advantages to juvenile sauropods when they were still small enough to be vulnerable. The specific speckled pattern across her back and flanks probably served species recognition and social communication functions. Modern large mammals that live in herds often show individual variation in coat patterns that helps herd members identify specific individuals. Modern reticulated giraffes have essentially fingerprint-unique coat patterns that allow individual recognition. Modern Gravy's zebras have similar individual pattern uniqueness. Diplodocus, who lived in herds of 5 to 12 animals based on trackway evidence, may have similarly used pattern variation for individual recognition among herd members. The Diplodocus reconstruction has broader implications for our understanding of sauropod coloration in general. If Diplodocus was patterned, then Brachiosaurus was probably patterned, Apatosaurus was probably patterned, Argentinosaurus was probably patterned. All of the great sauropods, from Jurassic through Cretaceous, were probably specifically coloured with individual pattern variation, rather than uniformly grey as older popular reconstructions have depicted them. The whole visual environment of the Mesozoic must be revised in light of this. The great herds of sauropods walking across Jurassic floodplains were not grey, they were patterned, they were colourful, they were visually distinctive in ways that older paleontology never appreciated. Breathe out. Watch a Diplodocus herd in your imagination, walking across a late Jurassic Morrison floodplain. Each animal shows her own specific pattern of darker and lighter patches across her back and flanks. The individual variation makes each animal recognizable to her herd members. The overall herd is a moving pattern of coordinated but individually distinct forms, walking together across the golden grass and dappled shade of the Morrison late afternoon. This is closer to what the actual late Jurassic sauropod herds looked like. Not grey uniform giants, but patterned individually distinct animals, each with their own specific coloration, participating together in the great sauropod herds that dominated the Jurassic terrestrial ecosystems. We are going to pause and honour an important honest limit on what we can know about dinosaur colour. The specific reconstructions we have walked through tonight are impressive achievements of modern paleontology, but they represent a small handful of exceptional cases. The vast majority of dinosaur species will never have their colours reconstructed. We should understand why. The melanosome analysis technique requires exceptional preservation of the original tissue. The specific microscopic structures that contain the pigment must survive intact from the moment of the animal's death through the entire fossilization process and into the modern era. This requires specific depositional environments that resist the normal chemical and physical processes that destroy soft tissue. The Yixian Formation of northeastern China is one such exceptional depositional environment. The specific combination of fine volcanic ash and lake mud that form the Yixian sediments resist the decomposition of organic matter unusually well. Feathered dinosaurs that died in the Yixian lakelands were often preserved with their feathers intact, including the microscopic melanosome structures within the feather barbules. The Clearwater Formation of Alberta is another exceptional environment. The specific tar-rich marine sediments preserved Borealopelta's body in its three-dimensional form, including microscopic skin detail. The Mother's Day Quarry in Montana is another exceptional site. The specific fine-grained lakebed sediments preserved Diplodocus skin fragments with sufficient microscopic detail for melanosome analysis. These are exceptional cases. Most dinosaur fossil sites do not preserve soft tissue in this level of detail. Most dinosaur fossils are bones only, with no skin or feather preservation of any kind, and even at the exceptional sites, only a small percentage of the specimens preserve enough microscopic detail for melanosome analysis. The result is that we have reconstructed colour patterns for perhaps a dozen dinosaur species out of the more than 1,100 known dinosaur species, roughly 1%. The other 99% will probably never have their colours reconstructed. This is a significant limit. Popular reconstructions of dinosaurs like Tyrannosaurus rex, Brachiosaurus, Stegosaurus, Ankylosaurus, Triceratops, and most other famous dinosaurs are still largely guesswork when it comes to their colours. We do not know what specific colours these dinosaurs wore. We do not have melanosome evidence from their preserved tissues. We can only make informed inferences based on comparison with modern animals of similar ecology. The informed inferences are not worthless. Comparison with modern animals suggests some likely patterns. Most large predators are countershaded. Most large herbivores show some pattern variation. Most tropical species have brighter and more varied colours than temperate species. Most nocturnal species have darker overall coloration. These patterns hold across many modern vertebrate groups and are probably true for extinct dinosaur species as well. But informed inferences are not the same as reconstructed evidence. We do not know that Tyrannosaurus rex was, say, dark green with darker stripes on his back and paler cream on his belly. This is a plausible reconstruction based on modern predator patterns, but it is not evidence-based. His actual colour could have been quite different. The honest limit is that most dinosaurs, in most popular illustrations, are being depicted in colours that reflect artistic interpretation rather than scientific reconstruction. The illustrations may still be beautiful and may still be reasonable guesses, but they are not in most cases based on actual colour evidence from the specific species. Sit with this. Hold the limit gently. The knowable dinosaur colours are exciting and beautiful, and we should honour them. The unknowable dinosaur colours are vast, and we should acknowledge the honest limit of what science can tell us. There are additional limits beyond just the preservation problem. Even when melanosomes are preserved, the analysis has specific technical limits. The technique reliably identifies black and brown pigmentation, produced by eumelanosomes and pheomelanosomes, but it does not identify all colours. Blue colours in modern animals are almost never produced by pigments. Instead, they are produced by specific structural arrangements of tissues that scatter blue light while absorbing other wavelengths. This structural blue is difficult to detect in fossil specimens because the specific structural arrangements are often destroyed by the fossilization process. Green colours in modern animals are similarly usually produced by combinations of blue, structural coloration, overlaid with yellow pigments. The yellow pigments themselves are usually carotenoids, which are dietary pigments that do not preserve in fossil melanosomes. So green colours, like blue colours, are largely invisible to melanosome analysis. Most red colours in modern birds are also produced by carotenoids, rather than by melanosomes. So bright reds, like the red of a modern cardinal, would not be reconstructible from melanosome evidence even if they were present in a fossil dinosaur. The specific range of colours that melanosome analysis can reconstruct is black, brown, reddish-brown, some greys, iridescent blues and greens, when the specific structural arrangements are preserved, and pale colours produced by melanosome absence, the range that cannot be reconstructed, bright reds, bright yellows, most greens, most blues, and any colour produced by carotenoids. This means that even for the dinosaur species with preserved melanosomes, the reconstructed colour pattern is only part of the total colour pattern. Additional bright colours may have been present that we cannot see in the analysis. Anchiornis, for example, may have had additional bright coloration in her display features that carotenoid pigments would have produced, and those colours are invisible to the current analytical techniques. Take a deep breath. The honest limit of the science is real. We know some dinosaur colours partially. We do not know most dinosaur colours at all. We should hold our current understanding humbly. But we should also be excited about what we can know. The specific reconstructions we have walked through tonight are real achievements. They tell us actual specific things about actual specific dinosaurs. They open up a window onto the visual surface of the deep past that older paleontology could not have imagined. We continue to walk. We honour what we know. We remain humble about what we do not know. We are about to walk slowly through the Yixian formation itself, because the specific depositional environment that preserved the melanosome evidence deserves a slower, more careful walk. The Yixian is one of the most important fossil-preserving environments in the entire history of vertebrate paleontology, and it is where most of the dinosaur colour reconstructions we have honoured tonight came from. The Yixian Formation is a rock unit exposed across northeastern China, particularly in Liaoning province and adjacent regions. The formation represents lake and lakeshore sediments deposited during the early Cretaceous, approximately 125 to 130 million years ago. The specific geological context that produced the Yixian preservation is unusual and interesting. The region was, at that time, a low-lying area with multiple shallow lakes and slow-moving streams. Volcanic activity in the surrounding highlands produced regular ashfalls that deposited fine volcanic material into the lake basins. The specific combination of ash and mud sedimentation created ideal conditions for preserving delicate organic tissues. When a small dinosaur died and fell into the lake, or when her body was washed into the lake by flooding streams, she was quickly buried by fine ash and mud. The rapid burial prevented decomposition and scavenging. The fine-grained sediment preserved microscopic detail of her feathers, her skin, and often her body outline. The result is that Yixian specimens preserve dinosaur bodies in extraordinary detail. Feather structure is preserved, skin patterns are preserved, body outlines are preserved, and, critically for our color reconstruction story, the microscopic melanosome structures within the feathers and skin are preserved. We are going to walk to a broader honouring of the specific fossil deposit tradition that produced most of the dinosaur color reconstructions. The Yixian Formation is part of a wider fossil preserving system called the Jehol biota, and the Jehol as a whole deserves recognition for its extraordinary contribution to dinosaur paleontology. The Jehol biota is the collective name for the fossil-bearing rocks of northeastern China that span the Middle Jurassic through the early Cretaceous, approximately 160 million to 120 million years ago. The specific rocks include multiple formations: the Yixian Formation we have been walking through, the Jufotang Formation, the Dabegu Formation, the Tiaojishan Formation, and various others. Together, these formations preserve one of the most diverse and well-preserved terrestrial ecosystems in the entire fossil record. The name Jehol comes from a historical region name for the northeastern part of China where the fossils are found. Modern geographers refer to the region as Liaoning Province, and adjacent parts of Hebei and Inner Mongolia. The specific deposit spans multiple hundreds of miles of exposed sedimentary rock across this region. The specific reason the Jehol preserves such abundant fossils is the combination of specific geological factors that we discussed for the Yixian. The region contained multiple shallow lake basins surrounded by volcanic activity. The specific ash falls from the volcanic eruptions periodically buried entire ecosystems in fine volcanic material that preserved delicate organic tissues. The specific ash and mud sedimentation continued for millions of years, producing multiple stratigraphic layers of preservation. The Jehol has produced an extraordinary range of fossil vertebrates. Multiple hundreds of feathered dinosaur species, many early bird species, numerous pterosaur species, various early mammal species, multiple amphibian and reptile species, various fish species. The diversity is remarkable. The specific colour reconstructions we have honoured throughout tonight are dominated by Jehol specimens. Sinosauropteryx is from the Yixian Formation of the Jehol. Microraptor is from the Yixian. Confuciusornis is from the Yixian and the Jufotang. Anchiornis is from the Tiaojishan, which is one of the lower Jehol formations. Various other reconstructed species come from Jehol deposits. Without the Jehol biota, dinosaur colour reconstruction as we know it today would essentially not exist. The specific preservation quality of the Jehol specimens has been the enabling condition for the melanosome analysis technique. Other fossil deposits can occasionally preserve similar detail, but no other deposit in the world produces the abundance and consistency of exceptional preservation that the Jehol produces. Settle into this. The Jehol biota is one of the most important paleontological resources in the entire world. The specific deposit has been intensively studied by Chinese paleontologists working with international collaborators for decades. Multiple thousands of specimens have been recovered. Hundreds of new species have been described. The specific contribution to dinosaur paleontology, and to feathered dinosaur paleontology in particular, has been transformative. The wider ecosystem picture that the Jehol reveals is one of the most complete pictures we have of any Mesozoic terrestrial community. We know the specific dinosaur diversity in remarkable detail. We know the specific bird diversity. We know the specific pterosaur diversity. We know the specific mammalian diversity. We know the specific plant community. We know the specific insect community. Together, all of this evidence produces a picture of the Jehol ecosystem that is more complete than nearly any other ecosystem in the entire fossil record. We can, in some sense, walk through the Jehol in a way that we cannot walk through most other Mesozoic ecosystems. The specific level of detail is extraordinary. The Chinese paleontological tradition that has recovered and studied the Jehol specimens deserves specific recognition. Chinese paleontologists have led most of the important discoveries. Xu Xing at the Institute of Vertebrate Paleontology and Paleoanthropology in Beijing has been particularly influential. His graduate students and colleagues have led many of the specific descriptions of new species. The specific institutional infrastructure of Chinese paleontology has been essential for the whole work. International collaborators have contributed substantially. Researchers from the American Museum of Natural History, from Yale, from Bristol, from various other institutions have worked with Chinese colleagues on the Jehol specimens. The collaboration has been fruitful, producing publications in the highest profile international journals across the past 20 years. Let this settle. Hold this gently. The Jehol biota is the specific fossil deposit that has made dinosaur colour reconstruction possible. The specific paleontological community that has worked on the Jehol deserves ongoing recognition for their achievements. Chinese and international researchers together have produced our current understanding of specific dinosaur colours. The Jehol continues to produce new specimens. New excavations are undertaken every field season. Additional species are described every year. Additional colour reconstructions are published regularly. The specific ongoing work will extend our understanding of dinosaur colour and dinosaur ecology across the coming decades. We should be grateful for this ongoing work. We should recognise the specific researchers who have made and continue to make important contributions. We should honour the specific fossil deposit itself for the extraordinary preservation quality that enables the work. The Jehol is one of the most important paleontological treasures in the world. The specific fossils it contains provide direct evidence of Mesozoic life that we cannot obtain from any other source. The specific research programs that study these fossils are producing understanding of the deep past that is transforming our picture of dinosaur biology. Hold the moment lightly. Watch the Jehol ecosystem in your imagination one more time. Not just the individual species we have honoured throughout tonight, but the wider community context. The multiple feathered theropod species, the multiple bird species, the multiple pterosaur species, the multiple mammal species, all of them participating together in the specific complex ecosystem that the Yixian and adjacent formations preserved. Every species has our own specific colours, whether we have reconstructed them or not. Every ecological interaction involves specific visual communication. Every daily activity uses specific coloration for specific purposes. The whole ecosystem is a symphony of specific colours and specific patterns and specific visual behaviours. The Jehol lived, in some quiet sense, 125 million years ago. It continues to be studied today. Its specific colours are gradually being recovered. The picture develops each year. We are grateful to be able to walk through it at all. We honour the specific fossils, the specific researchers, the specific deposit. There is one more theme worth mentioning about the Jehol. The specific ecosystem was affected by the specific volcanic activity that preserved it. Multiple eruptions across the millions of years of Jehol deposition periodically killed large numbers of animals. Ash falls covered entire forests. Pyroclastic flows destroyed specific communities. The whole ecosystem existed in the specific context of periodic volcanic disturbance. This means that many of the specimens we have from the Jehol are, in some sense, disaster fossils. They are animals who died in specific volcanic events. Their bodies were preserved because of the specific catastrophic circumstances of their deaths. The Yixian specimens especially reflect this pattern. The specific mode of death shaped the specific preservation. Animals killed by ash suffocation, for example, tended to be preserved in specific postures reflecting their last moments. Animals killed by pyroclastic flow heat tended to be preserved in different postures. The specific taphonomy of each specimen tells us something about the specific circumstances of the specific individual's death. There is something quietly moving about this. The specific individuals whose colours we can reconstruct today were, in most cases, victims of specific ancient catastrophes. Their deaths were traumatic. Their bodies were preserved precisely because they died in extraordinary circumstances that most animals do not experience. Their specific misfortunes have become, 125 million years later, the specific scientific opportunities that make dinosaur colour reconstruction possible. The tragedies of specific individual deaths in the deep past have become the gifts of specific scientific insight in the modern present. We honour them for this too. We honour the specific individuals who died specifically difficult deaths, and whose specific bodies contribute to modern scientific understanding as a result. We move on. The Yixian is not the only fossil site in the world that preserves this level of microscopic detail, but it is by far the most important for dinosaur colour reconstruction because of the specific abundance of feathered dinosaur specimens it has produced and the specific quality of the preservation. Take a deep breath. Let us walk through the Yixian ecosystem in imagination as it existed 125 million years ago before the deposition process that would eventually preserve so many of its animals. The landscape is a low-lying region with multiple lake basins surrounded by densely forested hillsides. The climate is warm temperate, with substantial rainfall throughout the year. The vegetation is dominated by conifers, particularly the tall cypress-like taxodium species that form the upper canopy. Below the canopy, various gymnosperm species filled the middle layers. Ferns and cycads covered the understory. Early flowering plants were just beginning to appear in some areas as the angiosperm radiation was starting. The lakes themselves supported abundant aquatic life. Small fish, aquatic invertebrates, amphibians, small aquatic reptiles. The lake edges were rich habitats for the many terrestrial vertebrates that came to drink and hunt at the water. The vertebrate community of the Yixian was one of the most diverse and best preserved early Cretaceous faunas in the world. Multiple species of small feathered theropods filled the small predator niches. Larger theropods hunted the medium-sized herbivores. Small ornithopods and other herbivores browsed through the understory. Early birds filled the aerial niches. Small mammals hunted in the leaf litter. Small reptiles filled various niches. Amphibians persisted in the wetter areas. The Yixian community was dominated in some ways by the diversity of small feathered theropods. Sinosauropteryx was there, running through the forest floor on her small hunts. Microraptor was there, gliding between the trees on her four wings. Anchiornis was there, perched on branches watching for prey. Sinosauropteryx was there, another dromaeosaur closely related to Microraptor. Various other small feathered species were also present, some named and some still awaiting formal description as new material is recovered. The larger theropods included several species. Yutyrannus huali was a large feathered tyrannosaurid, one of the most spectacular Yixian species, reaching lengths of 30 feet and weights of over 3,000 pounds. He is one of the largest known feathered dinosaurs, providing important evidence that feathers were not restricted to small theropods, but were present at various sizes across the theropod lineage. The Yixian community also included the small ceratopsian Psittacosaurus, who we honoured earlier for her colour reconstruction. Various other small ornithopod species were also present. The whole community was rich and varied, with substantial diversity at multiple size classes. The specific ecological interactions among these species produced a complex food web. The small feathered theropods competed with each other and with early birds for small prey. The medium-sized predators competed for medium prey. The large predators like Anchiornis targeted the largest prey species available. Small herbivores browsed on specific plant species. Larger herbivores targeted different plant species. The whole ecosystem was a mature, stable community with all major ecological niches filled. Settle for a moment. The Yixian ecosystem in its living form 125 million years ago was one of the most beautifully coloured ecosystems the deep past has produced. Every dinosaur species had specific coloration, though we can only reconstruct a few of them from preserved evidence. Every animal was participating in the visual communication of the community. Every social interaction, every predator-prey encounter, every mating display, every parental care event was visible in the specific colours that natural selection had shaped into each species. The visual richness we can partially reconstruct is just a small window onto what the actual visual richness must have been. If we could travel back to 125 million years ago and walk through a Yixian morning, we would see far more colour and pattern than the small handful of reconstructions we have honoured tonight. Every direction we looked would reveal new species with new specific colours. The whole ecosystem would be alive with visual signals we could barely process. We move slowly through the Yixian in our imagination. The morning is deepening. The mist is lifting from the lake surface. The small feathered theropods are active in the forest edges. The larger theropods are patrolling their territories. The small ornithopods are browsing in the understory. Every species is going about her daily activity in the specific colours that her species evolved. The Yixian is one of the most beautiful ecosystems paleontology has ever recovered. The specific challenges of Yixian paleontological work deserve their own quiet honouring. The specific fossil layers are exposed across a vast geographic area, but the specific fossil-bearing horizons are often thin and localised. Field workers must survey extensive rock exposures to find the specific spots where the exceptional preservation occurs. Once identified, the specific fossil sites require careful excavation techniques to preserve the delicate soft tissue evidence that makes the Yixian specimen scientifically valuable. The specific extraction of a well-preserved feathered dinosaur specimen from the Yixian rock is a substantial technical achievement. The rock matrix must be carefully removed without damaging the specimen. The specific feather impressions must be preserved. The specific soft tissue outlines must remain visible. The whole preparation process requires months of laboratory work for each specimen. Chinese museum preparators have developed the specific techniques needed for this delicate work. The specific institutional infrastructure at Chinese natural history museums includes specialized preparation laboratories staffed by highly skilled technicians. The specific work is not glamorous. It is patient, careful, technical, but it is essential for the scientific value of the Yixian specimens. Without the specific preparation work, the specimens would remain in their rock matrix and would not be available for scientific analysis. Without the scientific analysis, the specific colour reconstructions we have honoured throughout tonight would not exist. Every specific colour reconstruction rests on many hours of technical preparation work performed by Chinese museum staff, whose specific individual contributions rarely appear in the academic literature. We honour the specific preparators as well as the researchers. We move on. We are going to walk slowly through the specific principle of countershading, because it appears to have been one of the most widespread colour patterns across dinosaur species, and the pattern itself deserves a slower, more careful walk. Countershading is a colour pattern in which an animal's back is darker than her belly. The dark upper surface and the pale lower surface create a specific visual effect that helps hide the animal from predators looking at her from various angles. The specific mechanism works through the interaction of light and the animal's body shape. Animals in nature are typically lit from above, whether by direct sunlight or by scattered skylight. Under this overhead lighting, an animal's back receives more light than her belly. This creates a natural gradient of illumination across her body, with the back appearing brighter than the belly to any observer. For a uniformly coloured animal, this illumination gradient makes her body appear rounded and three-dimensional, and therefore more visible against a background. A predator looking at a uniformly coloured gazelle sees the specific rounded shape of her body clearly against the surrounding vegetation. The three-dimensional visibility helps the predator locate and target her. Countershading defeats this three-dimensional visibility. By making the back darker than the belly, countershading counteracts the natural illumination gradient. The darker back appears normal brightness under the brighter overhead illumination. The paler belly appears normal brightness under the dimmer bottom illumination. The overall effect is to make the animal's body appear more visually uniform, flatter, less three-dimensional, and therefore harder to see against the background. Modern animals show countershading across a remarkable range of species. Deer are countershaded, antelope are countershaded, fish are countershaded, with darker backs and pale bellies, an adaptation that helps hide them from both surface predators and deep water predators. Sharks are countershaded, whales and dolphins are countershaded. Even some invertebrates like squid and octopuses show functional countershading through their ability to actively change their skin coloration. The pattern is one of the most widespread predator avoidance color adaptations in the entire animal kingdom. The dinosaur countershading we have documented tonight extends this pattern back into the Mesozoic. Sinosauropteryx was countershaded. Anchiornis showed countershading combined with additional display coloration. Borealopelta was countershaded despite her extensive armor. Psittacosaurus was countershaded. Diplodocus was probably countershaded based on the analyzed skin fragments. The pattern appears to have been widespread across small and large dinosaurs, feathered and scaled dinosaurs, herbivorous and carnivorous dinosaurs. The evolutionary continuity of countershading across 400 million years of vertebrate life is remarkable. The specific selection pressure that shapes countershading, the vulnerability of terrestrial vertebrates to predators, is one of the most consistent selection pressures in the entire history of vertebrate evolution, and the specific solution that natural selection produces, the darker back and paler belly pattern, has emerged independently in multiple vertebrate lineages and has been preserved across immense stretches of geological time. Breathe slow. Watch a modern deer moving through a forest at dawn. Her back is dark brown. Her belly is pale cream. She's countershaded. She's difficult to see against the dappled forest floor. Her camouflage is helping her avoid detection by predators. Now imagine a Cretaceous Sinosauropteryx moving through her Yixian forest at dawn. Her back is reddish-orange. Her belly is pale cream. She is countershaded. She's difficult to see against the dappled forest floor. Her camouflage is helping her avoid detection by predators. The specific colours are different. The species are separated by 125 million years of evolution. But the fundamental countershading pattern is the same. The same visual principle is being applied to the same predator avoidance problem. The evolutionary continuity is direct. Sinosauropteryx did not invent countershading. She inherited it from earlier vertebrate ancestors, who had already evolved the pattern hundreds of millions of years before her time. She passed it on, through her lineage, to the true bird descendants who continue to use countershading today. Modern countershaded birds include most passerines, most raptors, and many waterfowl species. The specific dark back and pale belly pattern that Sinosauropteryx wore is essentially identical to the countershading pattern of a modern sparrow, a modern hawk, or a modern duck. The continuity from dinosaur to bird is direct and unbroken. Modern countershaded mammals include most large herbivores, many carnivores, and various smaller species. The mammals evolved countershading independently from the same selection pressures that shape the dinosaur pattern. We are about to walk to another important complication in dinosaur colour reconstruction. The colours we have discussed have been the colours of specific individual specimens at the specific life stages preserved in those specimens. but animals often change colour across their life stages. Juvenile animals often look different from adults. Breeding season adults often look different from non-breeding season adults. Old individuals sometimes look different from young adults. Modern birds show extensive age-related and season-related colour variation. Juvenile robins have spotted breast that they lose as they molt into adult plumage. Male mallards develop bright breeding plumage in autumn that they lose in summer molt into duller eclipse plumage. Older bald eagles develop their characteristic white heads only after several years of gradual colour transitions from all brown juveniles. Modern birds are, in many species, animals that wear different specific colours at different times of their lives. The dinosaurs probably showed similar patterns, but our colour reconstructions are typically based on single specimens at single life stages. We do not always know what the same species looked like at other life stages. For some species, we have limited information about age-related variation. Multiple Sinosauropteryx specimens have been analysed, ranging from juvenile to adult individuals. The specific colour patterns show some variation across life stages, though the general ginger and cream pattern appears to be relatively stable across the growth cycle. For other species, we have more limited information. Single specimens have been analysed. The specific colour patterns are known only for the specific life stage of that specimen. Other life stages remain unknown. The Anchiornis reconstruction is largely based on a single, well-preserved adult specimen. Whether juvenile Anchiornis looks substantially different from adults is unknown. Whether breeding season adults look different from non-breeding adults is unknown. The Microraptor reconstruction is similarly based on limited life stage sampling. The iridescent black pattern we know is the pattern of the specific specimens analysed. Other life stages are not yet documented. The Borealopelta reconstruction is based on a single specimen, though a very well preserved one. Whether other Borealopelta individuals showed the same specific colour pattern, or whether individuals varied substantially in coloration, is not yet known. The Diplodocus reconstruction is based on skin fragments from potentially multiple individuals but with limited life stage coverage. Whether juvenile Diplodocus looks substantially different from adults is unknown. Pause briefly. The specific colour reconstructions we have available are, in many cases, snapshots rather than complete portraits. They tell us how specific individuals looked at specific moments. They may or may not accurately represent the full range of coloration variation across the life cycle of the species. Modern research is beginning to address this issue by analysing multiple specimens of the same species across life stages. As more specimens are analysed, our understanding of within-species colour variation will develop. Eventually we may have reconstructions that show us how specific species looked at multiple life stages, from juvenile through adult through old age. For now, we should hold the current reconstructions with appropriate humility. They show us specific animals at specific moments. They do not necessarily show us the complete colour story of the species. There is also individual variation to consider. Modern animals within a species often show substantial individual variation in specific colour patterns. Modern deer within a herd show individual differences in coat pattern. Modern birds within a species show individual differences in specific feather markings. Modern reptiles within a species show individual differences in scale patterns. The dinosaurs probably showed similar individual variation. The specific colour pattern of a specific specimen may not be exactly representative of the species' overall pattern. Some individuals within a species may have been more brightly patterned, others may have been more subtly patterned. Some may have shown specific markings that others did not have. The specific melanosome analysis of a single specimen tells us about that specific individual. Broader inferences about the species require analysis of multiple specimens to determine the range of individual variation. We hold this gently. The specific colour reconstructions we have honoured tonight are real. They tell us real things about real animals, but they are, in some senses, samples rather than complete surveys. The full colour story of any dinosaur species requires more specimens than we currently have available for most species. We move on. The parallel evolution of the same solution across separate lineages tells us that countershading is a robust adaptation that natural selection strongly favours. The specific dinosaur countershading we have documented tonight is one small window onto this deep and widespread pattern. Every dinosaur species that has preserved skin evidence shows countershading in some form. The pattern was probably universal, or nearly universal, across dinosaur species. The uniform grey dinosaurs of older popular illustration were probably never a real dinosaur pattern. Real dinosaurs were almost certainly countershaded. We are going to pause for a quiet moment. We have honoured much of the dinosaur colour story tonight. The Sinosauropteryx ginger and cream tail, the Anchiornis rooster crest, the Microraptor iridescent black, the Confuciusornis pied wing pattern, the Borealopelta countershaded armour, the Psittacosaurus patterned flanks, the Diplodocus speckled skin, the Vinther research team and the technique they developed, the Ixion formation and its extraordinary preservation. We will walk through more of the story in the sections to come, but first, we should honour the walk we have already taken by pausing to breathe together in the quiet of the Cretaceous morning. Before we go any further, settle in. If this slow, calm way of wandering through dinosaur colour reconstruction helps you loosen your grip on the day, you're welcome to follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. Only if this kind of careful storytelling soothes you. There is no urgency. The decision can be as unhurried as a small coloured theropod pausing between morning hunts in her Yixian forest. For now, let your breath slow. The Sinosauropteryx is still moving through her morning mist. The Yixian ecosystem is alive with the specific colours that natural selection shaped into each species. The walk continues at the pace it needs to continue. Let the moment open. Watch the small feathered theropods for a long quiet moment. Their bodies are catching the morning light. Their specific colours are visible against the darker greens and browns of the forest floor and the vegetation. They are hunting, browsing, watching, communicating with each other through their specific reconstructed colour patterns. We're going to continue our walk soon. We're going to think more about the specific evolutionary origin of dinosaur colour. We will walk through the continuity from dinosaur colour to modern bird colour. We are going to bring our walk toward its slow, patient close. But for this quiet moment, we simply pause, we breathe. We rest with the beautifully coloured dinosaurs of the deep past. The Yixian morning holds us all. Take a deep breath. Hold this gently. The visual world of the Mesozoic was full of countershaded animals. Every dinosaur species we can imagine was probably participating in the same fundamental countershaded pattern. From the smallest feathered theropods to the great sauropods to the massive tyrannosaurs to the armoured ankylosaurs, all of them, almost certainly, wore some version of the dark back and pale belly pattern that modern deer and modern sparrows still wear today. The pattern is beautiful in its consistency. The same adaptive problem produces the same solution across immense evolutionary distances. The same countershaded appearance connects dinosaurs of the deep past to modern animals in your own present. The visual continuity across 400 million years of vertebrate evolution is one of the deepest patterns in the natural world. We are set to walk to one of the deepest and most beautiful continuities in modern biology. The colour connection between the dinosaurs of the deep past and the modern birds of your own present. Modern birds are, in strict taxonomic terms, dinosaurs. They descend directly from small feathered theropod dinosaurs of the late Jurassic and Cretaceous. The specific evolutionary transition from non-avian theropod to avian bird happened gradually across many millions of years, with intermediate species like Anchiornis, Microraptor, and Confuciusornis showing various combinations of ancestral theropod features and derived bird features. The transition eventually produced the true modern bird lineage that survived the KP extinction and radiated into the more than 10,000 modern bird species you know today. every sparrow, every robin, every hawk, every hummingbird, every eagle, every duck, every parrot, every penguin, every ostrich is a direct evolutionary descendant of small Cretaceous theropod dinosaurs. The specific colour mechanisms that modern birds use, the melanosome-based pigmentation we have discussed throughout tonight, are inherited directly from their theropod ancestors. Modern birds use melanosomes to produce black and brown colours. Modern birds use pheomelanosomes to produce red-brown colours. Modern birds use specific structural melanosome arrangements to produce iridescence. All of these colour mechanisms are essentially unchanged from the mechanisms used by Microraptor, Anchiornis, Sinosauropteryx, and Confuciusornis 125 million years ago. The evolutionary continuity is direct and unbroken. We are going to walk to a question that is important for understanding dinosaur colour. The colours we have reconstructed are the colours as they would appear to modern human vision. But dinosaurs did not have modern human vision. Their visual systems were different from ours. What their specific colours looked like to their own species members is a more complex question. Modern birds, the direct descendants of dinosaurs, have superb colour vision. Most birds have 4 types of colour-sensitive cone cells in their retinas, compared to the 3 types most humans have. The 4th cone type is sensitive to ultraviolet light, which is invisible to most humans. Modern birds see a range of colours that includes ultraviolet reflections, in addition to the visible spectrum humans can see. This means that many modern birds see specific coloration patterns that are invisible to human observers. The bright breeding plumage of some male birds includes ultraviolet reflections that make them appear substantially brighter to other birds than they appear to human eyes. The specific patterns of some bird species include ultraviolet elements that human observers do not perceive. The dinosaurs, based on the general phylogenetic position of the theropod bird lineage, probably had similar tetrachromatic colour vision. Their visual systems probably included ultraviolet sensitivity. Their perception of their own species' colour patterns probably included ultraviolet elements that would be invisible to us if we could somehow observe them directly. This has important implications for how we interpret dinosaur colour reconstructions. The reconstructions we have honoured tonight show us how the dinosaurs would have appeared to modern human observers. They do not necessarily show us how the dinosaurs would have appeared to each other. The Anchiornis rusty crest, for example, is probably accurately reconstructed as reddish-brown coloration produced by pheomelanosomes. But a fellow Anchiornis may have seen additional ultraviolet reflections on that crest that made it appear substantially brighter and more elaborate to their eyes than the reconstruction suggests to ours. The specific display value of the crest for Anchiornis social communication may have been considerably higher than the modern human reconstruction alone would indicate. Similarly, the Microraptor iridescent black we have honoured is probably accurately reconstructed, but a fellow Microraptor may have seen ultraviolet iridescent flashes in addition to the visible spectrum iridescence, making her body appear substantially more visually complex to them than to us. Rest in this. Hold this gently. The specific visual world of dinosaurs was probably richer than the reconstructions we have available today. The reconstructions capture the eumelanin and pheomelanin components accurately. We are about to walk to the Ixion at nightfall. Our long walk through dinosaur colour has been substantial. We should honour the animals as they settle into their evening rest, participating in the deep sleep behaviours we have honoured in other episodes of this channel. The Ixion forest is transitioning from day to night. The last light is fading through the conifer canopy. The specific colours of the small feathered theropods are becoming less visible as the light diminishes. Their patterned bodies fade into the darker shapes of dusk. Sinosauropteryx is settling into her chosen sleeping spot. She has spent the day hunting through the forest floor. Her ginger and cream body is barely visible now in the deepening dusk. She curls into her sleeping posture, her banded tail wrapped around her body, her feathered coat fluffed slightly for warmth. Her specific colours are still there. They are still real. but they are hidden by the dim light of the evening forest. Anchiornis is settling on her chosen perch high in the conifer canopy. Her rusty crest is barely visible now. Her pied wing feathers are dark shapes against the darker trunk of her sleeping tree. She tucks her head under her forelimb wing in the characteristic tucked bird sleeping posture we honoured in the sleep episode. Her specific colours are still there, they are just invisible in the dim light. Microraptor is settling in a sheltered spot within a tree crown. Her iridescent black feathers are dark on dark now. The iridescence needs specific bright light angles to be visible. In the dim dusk she looks simply dark, a small dark shape tucked into the tree canopy. Her specific structural coloration is still there. It is just not being displayed by the current lighting. Confuciusornis is settling on a lower branch. Her pied wing pattern is barely visible. Her long tail streamers hang down from the branch in soft dark curves. She tucks her head under her wing. Her specific colours are still there but not visible in the darkness. We're going to spend a long, quiet moment walking through a single day in the life of Sinosauropteryx. We have honoured her colours. We have honoured the specific research that reconstructed her patterns, but we should also honour her as a living animal, moving through her daily activities in her specific colours that natural selection shaped into her lineage. The morning we visit her began before dawn. She woke in her chosen sleeping spot, a small hollow beneath the roots of a large conifer at the edge of a small clearing. Her curled sleeping posture, similar to the tucked bird posture we have honoured in other episodes, kept her body warm through the cool early Cretaceous night. Her feathered coat trapped enough insulating warmth to allow her to sleep comfortably despite the temperature drop. As the pre-dawn light began to filter through the conifer canopy, she stirred. Her small body extended from the curled sleeping position. Her feathers fluffed to shake off the overnight dew. Her senses came online. Her large forward-facing eyes scanned the immediate surroundings for any threats or opportunities. She emerged from her sleeping hollow. She began her morning patrol of her small territory. Her territory was perhaps 3 or 4 acres of forest floor and forest edge habitat, containing enough small prey to support her energetic requirements. She patrolled it multiple times each day, learning the specific patterns of prey activity and updating her mental map of the microhabitats. Her ginger back caught the growing morning light as she moved. Her cream belly, hidden from most viewing angles, still contributed to her countershading. Her banded tail flicked behind her as she trotted through the ferns. She was, in her specific colours, moving through her ecosystem exactly as her species had evolved to do across millions of years of adaptation. She caught her first prey of the morning within about 20 minutes. A small lizard, hunting for insects in the leaf litter, failed to detect her approach because of her countershaded camouflage. She struck fast, caught the lizard behind its head with her sharp teeth, killed it with a single quick bite. She swallowed the lizard whole. She continued her patrol. Her second prey came within another 20 minutes, a cricket-like insect, larger than she usually took but within her prey size range. She snatched it out of the air as it tried to fly away. She ate it quickly, resumed her patrol. Her third prey was a small mammal, one of the small early mammalian species that shared the Yixian forest with the many dinosaur species. The mammal was slightly larger than her usual prey, weighing perhaps half as much as she did. She was excited to find it, because a mammal-sized meal would satisfy her for several hours. She stalked carefully, closed the distance, made her strike. She caught the mammal on her second attempt. She killed it with a specific bite to the neck. She dragged the body to a sheltered spot at the base of a fallen log and began to feed. She ate for perhaps 10 minutes, consuming most of the mammal's body. She left the head and part of the front limbs, unable to comfortably eat them. She would return to the leftover meat later in the day if she was still hungry, or she would leave it for the smaller scavengers who inevitably found any abandoned prey remains. Hold this moment. She's a real animal doing real things in her real ecosystem. Her specific colours are helping her succeed. Her countershading is keeping her hidden from potential predators. Her banded tail is confusing the specific prey species she hunts. Her overall pattern is well adapted to her specific ecological role. After her mammal meal, she rested through the middle of the day. The morning had been productive. She was well fed. She did not need to hunt again until the late afternoon or evening. She chose a sheltered spot at the base of a fern thicket, curled into a resting posture, and dozed through the warmest hours of the day. Her afternoon rest included brief periods of alertness, during which she scanned her surroundings for any changes. She was aware that predators of her own species existed in the ecosystem. Larger theropod species, including some of the smaller dromaeosaurs, would take her if given the opportunity. Her rest was therefore light rather than deep, allowing her to remain ready to flee at the first sign of danger. As the late afternoon light began to soften, she woke fully from her rest. She began her evening activity. She patrolled her territory again, hunting for additional prey. She caught 2 more small insects and 1 small lizard through the evening. She was satiated as the light began to fade toward dusk. She began to move toward her sleeping spot. She chose a slightly different spot from the previous night, following the general pattern of rotating between multiple safe sleeping locations to avoid becoming predictable to predators. She curled into her sleeping posture, her feathered coat fluffed for warmth, her eyes closed. The Ixian ecosystem transitioned into its nighttime mode around her. The insect chorus began. The nocturnal small mammals came out to hunt. The nocturnal theropod species began their own hunts. The whole forest was alive with different activity than the daytime activity we have been observing. She slept through the night. Tomorrow morning she would wake and repeat the cycle. She would continue this pattern for the natural span of her species' life, which was probably about 3 to 4 years for a compsognathed theropod of her size. Pause here. This was one specific day in her life. Multiplied across her 3 or 4 years of natural existence, this pattern repeated approximately 1,000 times. She hunted, rested, hunted again, slept. She did this for her entire life, until her death from predation, disease, or old age. She was a real animal, she lived a real life. Her specific colors were real. Her specific ecosystem was real. Her specific individual existence was one small point in the vast fabric of Cretaceous life. She has been dead for 125 million years. Her specific individual body decomposed shortly after her death. Her specific bones were probably scattered by scavengers before any fossilization process could preserve them. She left, in most cases, no direct evidence of her specific individual life, but her species left substantial evidence. Multiple Sinosauropteryx specimens have been recovered from the Ixian formation. Some of them preserved enough soft tissue for melanosome analysis. The specific individual whose colors we reconstructed was one specific individual of her species, and the reconstruction is based on the specific melanosome patterns preserved in her specific specimen. She is now honored in your imagination. The specific individual of her species who left the fossil we reconstructed is now the visual anchor for all of Sinosauropteryx paleontological understanding. She's become, in some quiet sense, one of the most famous individual dinosaurs in the modern paleontological literature. We honor her. We move on. Take a deep breath. Watch the whole ecosystem settle for the night. The bright-coloured animals of the daytime are becoming dark shapes in the darkening forest. Their specific colours do not disappear. They simply become invisible in the darkness. The animals themselves are still wearing their specific patterns. The patterns are just hidden. The Ixian night is deepening. The specific ecosystem sounds we discussed in the sleep episode are beginning. We are going to walk to the specific ecological principle of camouflage. We have discussed countershading as a specific pattern, but camouflage is a broader concept that encompasses many specific pattern types, and it deserves its own quiet walk. Camouflage is the general adaptation of animal coloration to reduce visibility against a specific background. The specific principle works by matching the animal's overall coloration to the general coloration of the background environment, and by breaking up the animal's specific outline with pattern variations that make her difficult to distinguish from surrounding vegetation or terrain. Modern animals show extensive camouflage evolution. Modern deer are camouflage for forest environments. Modern sandcats are camouflage for desert environments. Modern Arctic foxes are camouflage for snow environments. Every modern habitat has specific animals whose specific colorations are adapted for camouflage in that specific environment. The dinosaurs were probably similarly camouflaged. The specific color reconstructions we have honored tonight show specific evidence of camouflage adaptations. Sinosauropteryx's gingerback matched the reddish-brown color of fallen conifer needles on the Ixian forest floor. Borealopelta's countershaded body reduced her visibility to potential predators. Psittacosaurus's patterned flanks broke up her outline against dappled forest shadow. These specific camouflage patterns almost certainly had specific ecological consequences. Sinosauropteryx would have been more successful at hunting insects if her prey did not detect her approach. Borealopelta would have been safer from theropod predation if her outline was less visible from above. Psittacosaurus would have been less likely to be attacked by predators who could not clearly distinguish her from her background. The specific selection pressures that shape camouflage are strong. Predators who cannot see prey do not catch prey. Prey who are seen by predators do not survive to reproduce. The natural selection process favors specific colorations that reduce detectability. Across millions of years of this selection, specific coloration patterns evolve that are highly adapted for camouflage in specific environments. Breathe out. Let us think about the specific environmental context of Sinosauropteryx's camouflage. The Ixian forest floor was covered in fallen conifer needles, decaying leaves, and various decomposing plant material. The overall color palette was dominated by browns and reddish-browns, with some darker greens from evergreen understory plants and some greys from decaying wood. Sinosauropteryx's ginger back matched this general palette. Her body coloration blended with the specific colors of her environment. A predator looking down at her from above would have had difficulty distinguishing her specific body outline from the specific patterns of the leaf litter she was moving through. Her camouflage was effective. Her belly's counter-shaded pale color further reduced her visibility. From below, she appeared paler and more sky-like, less contrasted against the bright sky background. A ground-level predator looking up at her against overhead light would have had difficulty distinguishing her from the general bright background. Together, her counter-shaded back and belly provided specific camouflage protection from both aerial threats and ground threats. She was adapted for maximum ecological safety in her specific habitat. Other Ixian species show similar adaptations. Anchiornis's grey body matched the general grey-brown of the mid-canopy trunk and branches where she perched. Microraptor's iridescent black was inconspicuous in the deeper forest shadows where she hunted. Confuciusornis's pied pattern broke up her outline against the mottled sunlight and shadow patterns of the mid-canopy where she perched. Every specific Ixian species had specific camouflage adaptations for specific microhabitats. The ecosystem was full of specific animals whose specific colors matched their specific ecological contexts. The whole community was adapted for maximum visual efficiency in the specific Ixian environment. Modern ecosystems show similar patterns. Modern forest ecosystems are full of camouflaged animals. Modern grassland ecosystems are full of camouflaged animals. Every specific modern habitat has specific animals whose specific colors match the specific environmental palette. The evolutionary continuity from dinosaur camouflage to modern animal camouflage is direct. Sit with this. Watch the specific ecosystem you can imagine most clearly in your modern experience. A modern forest, perhaps, or a modern grassland, or a modern coastal environment. Every specific animal you can think of that lives in that ecosystem probably has specific camouflage adaptations for that specific environment. The same principle that shaped the specific colours of Sinosauropteryx shaped the specific colours of every camouflaged modern animal. The dinosaur camouflage we have reconstructed is one small window onto the vast continuous evolutionary story of camouflage across vertebrate life. The specific patterns we have documented are specific examples of a general principle that has shaped animal coloration for hundreds of millions of years. We honour the camouflaged Yixian dinosaurs. We honour the general evolutionary principle of camouflage. We honour the modern animals who continue to use the same specific principles to reduce their visibility in their specific environments. We move on, the insect chorus, the occasional small vertebrate rustling, the quiet breath of the sleeping animals. The forest is transitioning into its nighttime activity mode. This is one of the interesting features of dinosaur colour that we should acknowledge. The specific coloration only mattered when it was visible. Countershading only worked during the day, when predators could see the animals against illuminated backgrounds. Display coloration only worked when other animals could see it. The whole visual grammar of dinosaur coloration depended on adequate lighting. At night, the visual dimension of dinosaur biology substantially diminished. The animals still wore their specific colours, but the colours were largely invisible. Other communication modes became more important during the nighttime hours: vocalizations, scent signals, tactile interactions during close proximity. The rich daytime visual world was replaced by different sensory modalities. Modern animals show similar patterns. Modern colourful birds do not display their coloration at night. Their visual displays are timed to daylight hours. Their nighttime activities depend on other communication modes. The dinosaurs were probably the same. Their specific colour coordination in ecosystems was probably substantially daytime activity. The nighttime hours involved different behavioural patterns in which their specific colours were less important. Stay with this. The Yixian night is fully upon us now. The forest is dark. The specific colours we have honoured throughout tonight are no longer visible. The animals are sleeping in their chosen safe spots, their feathered bodies compact against the cool night air, their specific patterns quietly waiting for the morning to display again. They will sleep through the night. The Yixian ecosystem will continue in its quiet nocturnal activity mode. Small mammals will hunt through the leaf litter. Nocturnal insects will move in the canopy. The whole ecosystem will breathe in its nighttime rhythm. When the morning comes, the animals will wake. The specific colours will become visible again. The daytime visual world will resume. The Yixian ecosystem will restart its rich visual communication for another day. But for tonight, we are ending our walk here, in the quiet dark of the Yixian night, with the specific coloured dinosaurs sleeping in their chosen safe spots. With their patterns invisible but still real, we honour this. We move on to the close. But the ultraviolet components, which were probably present and probably ecologically important, are missing from our current reconstructions. The dinosaurs saw each other in ways we cannot see. The specific communication that flowed between individuals of the same species included visual signals that no modern human observer can perceive. This does not diminish the value of our current reconstructions. It simply reminds us that our reconstructions are partial. Even the specific species with well-documented melanosome evidence probably had additional visual features that we cannot detect. Modern bird species show us how substantial the ultraviolet component can be. Many species that appear relatively drab to human eyes reveal spectacular ultraviolet patterns when photographed with ultraviolet sensitive cameras. The species that appear brightly coloured to humans often show even more elaborate patterns when the ultraviolet is included. The visible spectrum coloration is only part of the story. Dinosaurs probably had similar patterns. The specific reconstructions we have documented tonight are the visible spectrum portion of dinosaur coloration. The ultraviolet portion is largely lost to us, though we know it was probably present based on the phylogenetic continuity with modern bird visual systems. Some modern research is beginning to explore whether ultraviolet-related structural coloration might be detectable in exceptionally preserved fossils. The specific tissue structures that produce ultraviolet reflections in modern birds are potentially preservable under some conditions. If preservation is sufficient, future analytical techniques might be able to reconstruct the ultraviolet components of dinosaur coloration. This is speculative and not yet demonstrated. The current techniques focus on eumelanin and pheomelanin identification, but the possibility of eventually detecting ultraviolet components is real, and future research may extend our reconstructions into this currently invisible portion of the dinosaur visual world. Take a deep breath. The world dinosaurs saw was probably richer than the world we can currently reconstruct. Their specific visual communication included dimensions we cannot yet access. But the specific colours we have reconstructed are still real. The dinosaurs really did wear the specific eumelanin and pheomelanin patterns we have documented. The reconstructions are accurate for what they cover, even if they do not cover the entire dinosaur visual world. We move on. Let this settle. Hold this gently. When you watch a modern crow flying across your modern sky, you're watching an animal that uses essentially the same colour mechanisms that a Microraptor used 125 million years ago. The specific iridescent black flashes of a crow's feathers are produced by the same structural melanosome arrangements that produce the iridescent black flashes of a Microraptor's feathers. The specific physical principle is unchanged. The specific biological mechanism is unchanged. The specific evolutionary lineage is continuous from Microraptor through Confuciusornis, through the early modern birds, through the entire modern crow radiation. You have never seen a Microraptor alive. She has been extinct for 125 million years, but you have seen her descendants in the form of every iridescent modern black bird you have ever observed. Modern crows, ravens, grackles, jackdaws, magpies, and various other blackbirds all use the same colour mechanism. All of them carry the deep evolutionary inheritance from small iridescent theropods of the Cretaceous. The specific mechanisms have been elaborated across the intervening 125 million years of bird evolution. Modern birds have developed new specific colour displays that Microraptor did not have. Modern birds have developed carotenoid-based coloration through dietary specialization that dinosaurs may not have had. Modern birds have developed the elaborate species-specific patterns that make modern bird identification the rich field it is, but the underlying colour mechanisms trace back through the dinosaur lineage. The specific melanosome technology, once evolved in the theropod ancestors of birds, has been continuously used by every descendant lineage ever since. Modern countershading traces back to dinosaur countershading. When you watch a modern deer, or a modern gazelle, or a modern hawk that is countershaded, you're watching an animal whose specific dark back and pale belly pattern uses the same fundamental mechanism that Sinosauropteryx used to hide from predators in the Yixian forest. The specific selection pressure has been continuous. The specific solution has been preserved. Modern display coloration traces back to dinosaur display coloration. When you watch a modern peacock displaying his tail feathers to a potential mate, you're watching an animal whose specific display grammar traces back through millions of years of bird evolution to the earliest display features documented in dinosaurs. The rusty crest of Anchiornis, the pied-wing pattern of Confuciusornis, the iridescent flashes of Microraptor, all of these represent the deep evolutionary origin of the visual display culture that modern birds have elaborated so spectacularly. Hold the moment lightly. The continuity from dinosaur colour to bird colour is one of the most quietly beautiful connections in modern biology. Every time you notice a bird in your modern world, you're noticing a direct evolutionary descendant of dinosaurs. The specific colours of that bird trace back through the evolutionary lineage to colour mechanisms that were present in Cretaceous dinosaurs. The visual world of modern birds is in some deep sense the visual world of the surviving dinosaur lineage. The other dinosaur lineages, the sauropods, and the ceratopsians and the great tyrannosaurs and the armored ankylosaurs all went extinct at the K-Peak boundary, their specific colour patterns went with them. But the small feathered theropod lineage survived, in the form of modern birds, and the specific colour mechanisms that lineage had evolved have been preserved and elaborated across the following 66 million years. Modern birds are, in some quiet sense, the visual heirs of the entire dinosaur legacy. We are about to walk to the modern bird world in more detail. The dinosaur colour continuity we honoured earlier deserves a slower walk through what modern bird colours actually look like, because they are the specific descendants of the dinosaur colours we have been reconstructing. Modern birds show one of the most spectacular colour diversities in the entire animal kingdom. Over 10,000 modern bird species exist. Every one of them wears specific colour patterns evolved across the intervening 66 million years since the KP extinction. Many of them wear colours so elaborate and so specific that identifying birds by their coloration is a legitimate hobby that people spend lifetimes learning. The specific colour mechanisms of modern birds include everything we have discussed for dinosaurs plus additional elaborations. Eumelanin-based black and brown coloration, pheomelanin-based reddish-brown coloration, iridescent structural coloration from specific melanosome arrangements, countershading for predator avoidance, display coloration for social communication, plus carotenoid-based bright colours that dinosaurs may or may not have had, plus various additional structural coloration mechanisms that produce blues, greens, and various complex colour patterns. Let your breath slow. Let us think about a few specific modern bird examples that illustrate the colour diversity. The peacock. Male peafowl, particularly the Indian peafowl, familiar in modern zoos and parks, show one of the most spectacular colour displays in the entire animal kingdom. His tail feathers extend to a train several feet long, covered in the famous eye spot pattern that consists of iridescent blue, green, and gold structures. The specific colours are produced by a combination of eumelanin-based coloration, structural iridescence from melanosome arrangements, and possibly some carotenoid contributions. During his breeding display, he raises the train into a spectacular fan and vibrates the feathers to produce a shimmering visual effect. The whole display is one of the most elaborate visual signals in all of vertebrate biology. The peacock evolved from theropod dinosaur ancestors. His specific display grammar traces back through modern galliform bird evolution to smaller pheasant-like ancestors, back through earlier bird lineages, back through the small feathered theropods of the Cretaceous. The evolutionary lineage that produced his elaborate display started with the more modest display features of species like Anchiornis and Confuciusornis. The hummingbird. Modern hummingbirds are among the smallest birds in the world. Many species show extraordinary iridescent coloration in specific body regions, particularly in the throat patches of males. The specific colours, produced by structural coloration mechanisms similar to those we identified in Microraptor, shift dramatically depending on the angle of light and the angle of observation. A hummingbird throat patch can appear brilliant ruby red at one angle, deep black at another angle, and flash with additional colours as the bird moves. The specific iridescence of hummingbirds traces back through the bird lineage to the general structural coloration mechanisms that Microraptor was already using 125 million years ago. The specific hummingbird elaboration is spectacular, but the underlying mechanism is directly inherited from ancestral dinosaur colour technology, the parrot. Modern parrots show extensive bright coloration through combinations of structural mechanisms and carotenoid pigments. The specific bright greens, blues, reds, and yellows of modern parrots are among the most striking colours in the modern bird world. The specific colour patterns often serve species recognition and display functions in the complex social structures of parrot flocks. The specific parrot coloration relies on colour mechanisms that may not have been present in dinosaurs. The bright carotenoid components are almost certainly bird-specific evolutionary developments. but the underlying melanin components and the structural coloration mechanisms trace back to dinosaur ancestors. The specific ecological context of modern parrots is worth pausing over. Modern parrots are highly social animals. Many species live in large flocks of dozens or hundreds of individuals. The specific complex social structures require sophisticated visual communication systems. The specific bright coloration of modern parrots functions in this social context, allowing rapid species and individual recognition within complex flock dynamics. The specific social communication systems of modern parrots probably evolved gradually after the KPG extinction. Non-avian dinosaurs may or may not have had similarly complex social communication systems, requiring similarly bright coloration. The specific evolutionary path from the modest display colours of species like Anchiornis to the elaborate flock communication colours of modern parrots involves substantial elaboration across 66 million years of bird evolution. The whole trajectory is interesting. Simple display features in some dinosaur species, gradual elaboration across the early bird lineages, explosive diversification after the KPG extinction cleared the way for bird radiation, ongoing refinement of visual communication systems throughout the Cenozoic, the eventual arrival at the spectacular colour diversity of modern parrots and other elaborately coloured bird groups. At each stage of this trajectory, specific ecological pressures shape specific coloration patterns, camouflage against specific predators, display for specific mating strategies, recognition for specific social structures. All of these pressures accumulated across evolutionary time to produce the specific modern bird colour diversity we can observe today. The dinosaur origin of this trajectory is real and important, but the specific modern elaborations are also real and important. Both aspects of the story deserve their own recognition. The bird of paradise. Modern birds of paradise show some of the most elaborate display coloration in the entire bird world. Male birds of paradise perform extraordinary courtship displays involving specific coloration, specific body postures, and specific movement patterns coordinated into complex ritual behaviours. The specific colours combine multiple mechanisms including iridescence, carotenoid pigments, and structural coloration. The specific bird of paradise displays represent the extreme elaboration of the dinosaur display coloration tradition. The specific display grammar has been amplified across millions of years of evolution into extraordinary complexity. But the underlying tradition of using specific colours for display communication traces back through the entire bird lineage to the modest crest displays of species like Anchiornis. Settle for a moment. The modern bird world is the living continuation of dinosaur colour evolution. Every specific modern bird species inherits the general colour mechanisms that dinosaurs developed. Many species elaborate those mechanisms in ways that dinosaurs never quite achieved. Some species use colour mechanisms that may be bird-specific evolutionary developments after the KPG extinction. But the whole modern bird colour diversity is, in some deep sense, the ongoing story of dinosaur colour evolution. It did not end with the KPG extinction. It has continued for 66 million years since, producing the spectacular colour diversity you can observe in any modern natural environment. Every bird you notice tomorrow in your modern world is a specific descendant of dinosaurs, wearing specific colours that trace back through the evolutionary lineage to the dinosaur colour mechanisms we have honoured tonight. We honour this continuity, we move on. We are going to walk to the specific question of carotenoid-based coloration. This is one of the most important components of modern bird coloration, and it is one of the components we cannot reconstruct in dinosaurs. Carotenoids are pigment molecules that modern birds acquire through their diet. The specific carotenoids that produce bright red, orange and yellow colours in modern bird feathers come from plant sources. Birds eat fruits, seeds, or insects that contain carotenoids. The birds absorb the carotenoids and deposit them in specific feathers to produce specific colours. The specific bright red of a male northern cardinal is produced by carotenoids acquired through his diet of specific fruits and seeds. The specific bright yellow of a male American goldfinch is produced by carotenoids from his summer diet of thistle seeds and other yellow carotenoid-rich plants. The specific orange of a male oriole is produced by carotenoids from his diet of nectar and fruits and insects. Modern birds show extensive carotenoid-based coloration. Many of the most visually striking modern bird species owe their bright colours to carotenoids. Modern parrots, modern hummingbirds, modern various finch species all show carotenoid coloration. But carotenoids do not preserve in fossils. The specific molecules decompose within days or weeks of death. No carotenoid evidence can be recovered from any dinosaur specimen, regardless of preservation quality. This creates an important gap in our dinosaur colour reconstructions. If dinosaurs had carotenoid-based coloration, and if that coloration was as visually significant in their species as it is in modern bird species, then our reconstructions are missing an important part of what dinosaurs actually looked like. Whether dinosaurs actually had carotenoid-based coloration is a complex question. Modern birds acquired their carotenoid deposition capability at some point in bird evolutionary history, but the exact origin of this capability is not well documented. The specific enzymes and metabolic pathways involved in carotenoid deposition into feathers may have evolved after the KPG boundary, in which case dinosaurs may not have had significant carotenoid coloration, or the capability may have evolved earlier, before the KPG boundary, in which case at least some dinosaur species may have had bright red, orange or yellow coloration produced by dietary carotenoids. The current best evidence suggests that at least some dinosaurs probably had some carotenoid coloration. Modern birds show carotenoid deposition capabilities across a wide range of species, suggesting that the capability may have evolved relatively early in bird evolutionary history and may have been present in at least some pre-KPG dinosaur species. But the specific dinosaur species that had carotenoid coloration and the specific colour patterns they wore are largely unknown. Take a deep breath. This means that our reconstructions of specific dinosaur species may be missing bright red, orange, or yellow elements that were actually present in the living animals. Anchiornis' rusty crest, which we have reconstructed as pheomelanin-based reddish-brown, might have had additional bright red carotenoid elements that intensified the display effect. Sinosauropteryx's tail bands might have included yellow or orange carotenoid highlights that we cannot detect. The specific bright colours of dinosaur display features may have been more elaborate than the melanosome-only reconstructions suggest. The reconstructions capture the eumelanin and pheomelanin components, but any carotenoid components are lost. This does not diminish the value of our current reconstructions. The eumelanin and pheomelanin components are still real. The specific reconstructions are still accurate for what they cover, but we should hold the reconstructions with awareness that the actual dinosaurs may have been more brightly coloured than the current reconstructions can show us. Modern research is exploring various approaches to detecting non-melanosome colour mechanisms in fossils. Some techniques may eventually be able to detect specific structural coloration mechanisms. Others may be able to detect chemical residues of carotenoid molecules. Neither approach is fully developed yet, but future work may extend our understanding of dinosaur coloration beyond the current melanosome-based reconstructions. For now, we hold the current reconstructions as they are: real, accurate for what they cover, incomplete for the specific colour mechanisms they cannot detect. The dinosaurs were probably more coloured than we can currently show, but what we can show is still substantial. The specific reconstructions we have honoured tonight are the beginning of dinosaur colour understanding, not the end. The field will continue to develop across the coming decades. We move on. They carry forward the colour technology that dinosaurs developed. They elaborate it into the spectacular colour displays that make modern bird watching one of the most rewarding activities in natural history. We honour this continuity. We move on. we will walk to the other major function of dinosaur coloration. Countershading provides predator avoidance advantages, but dinosaurs also use specific display colors for social communication with other members of their own species. Display coloration is one of the most widespread color functions across modern vertebrates. Modern birds show the most spectacular display coloration, with elaborate mating displays involving bright colors, complex patterns, iridescent flashes, and coordinated movements. Peacocks display their tail feathers. Birds of paradise perform their extraordinary courtship dances. Male ducks show bright breeding plumage. Male grouse display their inflated air sacs. Modern birds use color for display in ways that are among the most elaborate visual communication systems in the entire animal kingdom. Modern reptiles show more modest but still significant display coloration. Male lizards develop brighter breeding colors during mating season. Some snake species show specific display patterns. Some crocodilians show coloration changes during breeding periods. Modern mammals show display coloration in various species, particularly primates who have highly developed color vision. Male mandrills display their bright red and blue facial coloration. Various primate species show breeding-related color changes. The dinosaurs, based on the color reconstructions we've walked through tonight, show display coloration in patterns that are consistent with the modern bird and modern reptile approaches. The specific display features we can document include the rusty crest of Anchiornis, the iridescent structural coloration of Microraptor, the specific banded tail of Sinosauropteryx, and the complex pattern variation across the flanks of Psittacosaurus and Diplodocus. These display features probably served specific communication functions. The rusty crest of Anchiornis was almost certainly a mating display feature. Modern birds with similar crests, like modern male mallards or modern male roosters, use their crests in mating displays to attract females. The crests are often more elaborate in males than in females, and are enlarged during breeding season. Anchiornis probably followed a similar pattern. The iridescent coloration of Microraptor was probably a species recognition and mating display feature. Modern iridescent birds like crows and ravens use their iridescence for social communication with other members of their species. The specific angle-dependent color shifts help birds recognize members of their own species and assess the physical condition of potential mates. Microraptor probably used her iridescence for similar functions. The specific banded tail of Sinosauropteryx may have served multiple functions. The banded pattern probably helped confuse pursuing predators by breaking up the outline of her tail during fast movement. But it may also have served display functions for social communication with other Sinosauropteryx, particularly when the tail was raised or moved in specific display postures. The complex flank patterns of Psittacosaurus and Diplodocus probably included both camouflage functions and social recognition functions. Modern large mammals that live in herds show similar dual-function pattern variation, with the patterns providing both camouflage against predators and individual recognition for herd members. Pause briefly. The visual world of the Mesozoic was probably full of display coloration. Every dinosaur social interaction, from mating displays to territorial encounters to parental care of young, probably involved some component of color communication. The dinosaurs saw each other, and they saw each other in specific ways that carried specific social meanings. Modern birds show us how elaborate this can become. A modern peacock's tail display is not just biological equipment. It is an elaborate visual message being transmitted to potential mates, potential rivals, and any other peacocks who happen to be watching. The specific colors, the specific patterns, the specific movements all combine into a communication event that has evolved across millions of years of peacock lineage evolution. The dinosaurs almost certainly participated in similar communication events. We do not have direct evidence of specific dinosaur display behaviors, because behavior does not fossilize, but we have the color reconstructions that show the specific display features. We have the ecological inference that display coloration served the same general functions in dinosaur ecosystems that it serves in modern ecosystems. we have the phylogenetic continuity that connects dinosaur display coloration to modern bird display coloration. Together, these lines of evidence suggest that dinosaur social behavior was probably richly colored and visually complex. Males displayed to attract mates. Females made choices based on the specific quality of male displays. Rivals assessed each other through visual communication. Parents identified their young through specific patterns. Young identified their parents through similar patterns. The whole social fabric of dinosaur communities was probably held together in part by continuous visual color communication. Let the moment open. Watch a Yixian forest evening in your imagination. The small feathered dinosaurs are engaged in various display activities. An Anchiornis male raises his rusty crest and performs a small dance on his branch. A female Anchiornis on a nearby branch watches. A male Microraptor spreads his forewings to show off his iridescent black and blue coloration. A female Microraptor observes him. A group of Sinosauropteryx are gathered near a stream, their banded tails flicking in various display postures as they communicate specific messages to each other. The forest is full of visual signals. The animals are communicating with each other. The specific colors we have reconstructed are being used in real time in the deep past to convey specific meanings to specific other animals. This is what dinosaur social life probably looked like. Not silent color-neutral interactions, but vivid, visually rich communication events that used the specific display coloration that natural selection had shaped into each species. We're going to walk to the question of when the specific dinosaur color mechanisms first evolved. The melanosome-based color patterns we have documented tonight are ancient, but exactly how ancient are they? What can we say about the evolutionary origin of dinosaur coloration? Melanosomes as a general vertebrate feature are very ancient. The specific cellular organelles that produce black and brown pigmentation in modern vertebrates were probably present in the common ancestor of all vertebrates, hundreds of millions of years ago. Every vertebrate lineage since then has inherited and used melanosomes for pigmentation. Fossil evidence for melanosome preservation in specific pre-dinosaur groups is available. Fossil fish from the Devonian preserve melanosome evidence. Fossil early amphibians preserve melanosome evidence. Fossil early reptiles preserve melanosome evidence. The technique of melanosome analysis, developed originally for dinosaur color reconstruction, has been extended to older vertebrate groups and has produced color reconstructions for various pre-dinosaur species. The specific dinosaur pigmentation patterns we have documented tonight are therefore not evolutionary novelties. They inherit from much older vertebrate color mechanisms. Sinosauropteryx did not invent countershading. She inherited it from ancestors who had been countershaded for hundreds of millions of years. What is specifically dinosaur about dinosaur coloration is the specific evolutionary elaborations that occurred within the dinosaur lineage. The specific display features the Anchiornis wore, the specific iridescence of Microraptor, the specific pied pattern of Confuciusornis. All of these represent evolutionary specialization of the general melanosome pigmentation system that dinosaurs inherited from their pre-dinosaur ancestors. The evolutionary origin of dinosaur feathers is directly relevant here. Dinosaurs did not always have feathers. The specific evolutionary origin of feathers appears to have been in the early theropod lineage, perhaps in the late Triassic or early Jurassic. Before feathers evolved, dinosaurs had scaly skin similar to modern reptile skin. The specific color mechanisms available to scale-covered dinosaurs were similar to those of modern reptiles. When feathers evolved, they opened up new possibilities for color display. Feathers can be structured to produce iridescence in ways that scales cannot. Feathers can carry specific pigment patterns in ways that scales cannot. Feathers can be elaborated into display features like crests and wing patterns that scale-covered animals cannot easily produce. The feathered theropod lineage therefore had access to visual display technology that non-feathered dinosaur groups did not have. This is one reason why the specific color reconstructions we have tonight are dominated by small feathered theropods and their close relatives. The specific preservation is one factor, but the actual biology is another. Feathered theropods had more elaborate coloration than non-feathered dinosaurs, and their color patterns were probably more evolutionarily significant for their social behaviors. Soft and slow. The evolutionary origin of the specific dinosaur color displays we have documented is a fascinating research question in its own right. When did iridescent structural coloration first evolve in the theropod lineage? Which specific theropod species were the first iridescent dinosaurs? What was the ancestral color pattern of the Paravian lineage that produced Anchiornis, Microraptor, and Confuciusornis? These questions are actively being researched. Additional specimens are being analyzed. Additional analytical techniques are being developed. Our picture of the evolutionary origin of specific dinosaur color mechanisms will continue to develop across the coming decades. The current best interpretation is that iridescent structural coloration probably evolved somewhere in the Paravian lineage, perhaps in the Middle or Late Jurassic. Microraptor's iridescence is one of the earliest documented examples, but earlier iridescent species probably existed. The specific evolutionary origin may be pushed further back as additional specimens are analyzed. Countershading is older than iridescence. The specific dark back and pale belly pattern was probably present in dinosaurs from the beginning of the dinosaur lineage, inherited from their pre-dinosaur reptilian ancestors. Every dinosaur species that has preserved skin evidence shows countershading, suggesting that the pattern was universal across dinosaurs from the earliest Triassic species through the latest Cretaceous species. Display coloration probably evolved multiple times independently in different dinosaur lineages. The specific display features seen in various species probably reflect independent evolutionary innovations rather than a single ancestral display pattern. Different lineages evolved different specific display features to fit their specific social behaviors and their specific ecological contexts. The whole picture is one of complex evolutionary dynamics playing out across the dinosaur lineage. Multiple ancestral color mechanisms were inherited from pre-dinosaur ancestors. Multiple specific elaborations evolved within different dinosaur lineages. The result was a diverse and specialized visual world, in which different dinosaur species wore different specific color patterns adapted to their specific ecological roles. Modern birds inherit this complex color history. The specific colors of modern birds trace back through the intricate evolutionary history of dinosaur coloration. Every specific color pattern in a modern bird lineage has some ancestral origin somewhere in the dinosaur or pre-dinosaur past. We are set to walk to the question of how the dinosaur color reconstructions have affected the modern practice of paleoart. Paleoart is the specific artistic tradition of illustrating extinct animals based on scientific evidence and reasonable inference. The tradition has a long history reaching back to the earliest days of dinosaur paleontology in the 19th century. The traditional paleoart of the 19th and 20th centuries depicted dinosaurs in specific color palettes that reflected the artistic conventions of those periods. The earliest paleoart, produced in the middle 19th century by artists like Benjamin Waterhouse Hawkins, depicted dinosaurs in relatively drab grey-green colours, similar to the depicted colours of modern lizards and crocodiles. The paleoart of the early 20th century, produced by artists like Charles R. Knight, continued the general grey-green tradition, but with more sophisticated attention to specific anatomical detail and to the specific ecological context of each species. Knight's dinosaurs are more scientifically accurate than the earlier Hawkins reconstructions, but they are still coloured in the general grey-green palette that reflected the assumption that dinosaurs looked like modern reptiles. The middle 20th century paleoart continued this tradition. Zdeněk Burian in Czechoslovakia produced some of the most influential dinosaur illustrations of the period, showing dinosaurs in dramatic natural settings with the traditional grey-green coloration. The specific style influenced generations of subsequent paleo artists. The dinosaur renaissance of the 1970s and 1980s brought some changes to paleo art. Some artists began experimenting with more varied colour palettes, particularly for the smaller and more active dinosaurs that the Renaissance was reimagining as bird-like rather than reptile-like. But the general grey-green tradition remained dominant for most large dinosaur species. The 2010 Sinosauropteryx colour reconstruction was one of the events that began transforming paleo art in more substantial ways. For the first time, artists had evidence-based colour reconstructions for specific dinosaur species. Sinosauropteryx could be legitimately depicted with her ginger and cream tail pattern because the specific pattern was documented in the fossil evidence. Modern paleo art, produced in the 2010s and 2020s, has increasingly incorporated the specific colour reconstructions we have honoured tonight. Sinosauropteryx is now routinely depicted with her banded ginger tail. Anchiornis is depicted with her rusty crest and pied wings. Microraptor is depicted with her iridescent black feathers. Borealopelta is depicted with her countershaded armour. Modern paleo art is more colourful than the traditional grey-green paleo art of the 20th century. The change has been substantial but not complete. For the species with reconstructed colours, modern paleo art is now generally evidence-based. For the many species without reconstructed colours, modern paleo art remains speculative, though often with more colour variation than the traditional grey-green palette. Take a deep breath. The transformation of paleo art is one of the most visible consequences of the melanosome analysis work. The specific pictures that people see of dinosaurs in modern books, modern documentaries, modern children's illustrations are now often based on evidence-based colour reconstructions where the reconstructions exist. This affects how modern people think about dinosaurs. A generation of children growing up with the newer paleo art is developing mental images of dinosaurs that are substantially more colourful than the mental images their parents developed from the older paleo art. The visual imagination of the modern public about dinosaurs is being reshaped by the colour reconstruction work. Specific paleo artists have been particularly influential in this transformation. John Conway, in the United Kingdom, has produced influential modern paleo art that incorporates the specific colour reconstructions along with sophisticated attention to specific anatomical detail. Emily Willoughby in the United States has produced influential illustrations of the small feathered theropods with careful attention to the reconstructed colours. Mark Whitten, also in the United Kingdom, has produced influential paleo art across many dinosaur groups. Julius Chotogny in Canada has produced influential work particularly on the Cretaceous North American dinosaurs. The specific artists have their own individual styles and their own individual interpretations, but they all work within the general framework of evidence-based paleo art that the melanosome analysis has enabled. The specific colours of their illustrations, when the species of reconstructed colours available, reflect the specific fossil evidence. There is also modern popular art that draws on the same tradition. Modern children's dinosaur books now often feature more colourful dinosaurs than earlier generations of children's books. Modern museum exhibits sometimes feature reconstructed colour displays of specific species with documented colour patterns. Modern documentary programs increasingly feature the specific colour reconstructions in their visualizations of dinosaurs. The whole visual culture of dinosaurs is being transformed by the colour reconstruction work. Not overnight, not everywhere, but gradually and substantially. The picture of dinosaurs that most people carry in their minds is becoming over time more accurately coloured. Hold this moment. Watch a modern paleo art illustration of Sinosauropteryx in your imagination. Her ginger back, her cream belly, her banded tail, her specific colours depicted according to the specific fossil evidence. This is what dinosaur illustration is beginning to look like in the 2026 paleo art tradition. Compare this to the grey-green Sinosauropteryx that older paleo art would have depicted. The difference is substantial. The modern illustration is more accurate. It is more scientifically grounded. It reflects specific evidence from specific specimens, rather than general assumptions about what dinosaurs might have looked like. This is progress. This is what evidence-based paleontological illustration should look like. This is what the melanosome analysis work has enabled. We're going to walk through one more specific aspect of dinosaur colour. The Cretaceous morning we visited earlier was bright and coloured, but dinosaurs also existed in darker environments, and their coloration in those environments deserves its own quiet walk. Some Yixian dinosaurs lived in the darker forest interior, where less sunlight penetrated the canopy. Some Cretaceous dinosaurs from other formations lived in dense forest environments, where the light was substantially dimmer than in the more open Yixian habitats. Some dinosaurs lived in nocturnal or crepuscular niches, where they were primarily active during low-light hours. The specific coloration of these dark environment dinosaurs would have been adapted for their specific low-light contexts. Modern nocturnal animals show specific coloration patterns that differ from diurnal animal coloration. Modern nocturnal predators tend to have darker overall colours that make them less visible in dim light. Modern nocturnal prey species tend to have similar dark overall colours. The dinosaurs probably followed similar patterns. Small nocturnal theropods that hunted in the deep forest at night probably had darker overall coloration than their day-active relatives. Small nocturnal ornithopods and other prey species that were active at night probably had similar dark colorations. The specific colour reconstructions we have discussed tonight are dominated by day-active species from the Yixian and similar well-lit environments. But many dinosaur species probably lived in darker environments, and their specific colours are probably harder to detect through melanosome analysis because the analysis works best for specific colourful patterns rather than for uniformly dark colorations. Pause here. The specific dark environment dinosaurs are one of the least honoured groups in the current colour reconstruction literature, but they probably existed in substantial numbers. Every dinosaur ecosystem probably had some dark environment specialists. The whole nocturnal or crepuscular niche was probably occupied by specific dinosaur species with specific dark colorations. Some direct evidence exists for nocturnal dinosaur species. Certain small troodontids show anatomical features consistent with nocturnal hunting, including large eyes optimized for low-light vision. Some small dromaeosaurs may have been similarly adapted. The specific ecological niches for nocturnal small theropods were probably filled in most Cretaceous ecosystems. The specific coloration of these nocturnal specialists is largely unreconstructed. Most known troodontids and small dromaeosaurs have not had colour reconstructions published. When they eventually do have reconstructions, we expect to see specific dark colorations adapted for low-light hunting. Let your shoulders drop. Watch a Yixian night in your imagination. The forest is dark. The Cretaceous moon provides some illumination through gaps in the canopy. The specific nocturnal dinosaurs are active, hunting through the dim understory. Their specific dark colorations make them nearly invisible in the low light. They are efficient hunters of the specific small prey species that share their nocturnal niche. The Yixian nighttime hunters would probably have included specific troodontid species. Small dromaeosaurs may have been active at least during dawn and dusk. Various small mammals were certainly active at night. The whole nocturnal ecosystem was rich with specific animals, adapted for low-light activity. The specific colours of these nighttime dinosaurs remain to be reconstructed. Future paleontological work may recover melanosome evidence from specific nocturnal specimens. The specific dark colorations we can predict from ecological principles may eventually be confirmed by specific fossil evidence. For now, we honour them as inferred rather than reconstructed. The Yixian night is full of specific dark-coloured animals whose specific patterns we cannot currently see, but whose specific ecological role is clear from other evidence. Breathe out. Hold this gently. The full-colour story of dinosaurs includes not just the bright reconstructed species we have honoured throughout tonight. It also includes the dark nocturnal species we can only partially imagine. It includes the wide range of specific coloration adaptations for specific environmental contexts. The whole picture is much more complete than the current reconstructions alone can show. Every ecosystem, every microhabitat, every specific ecological role was probably filled by specific dinosaur species with specific coloration adaptations. The visual world of the Mesozoic was as varied as the visual world of modern animal communities. We honour the current reconstructions for what they show. We honour the wider picture that they only partially reveal. We are grateful for what modern science has been able to reconstruct and humble about what remains to be discovered. We move on toward the close. We honour the specific artists who have participated in this transformation. We honour the specific children who will grow up with more accurately coloured dinosaurs in their imagination. We honour the specific researchers whose work makes evidence-based paleo art possible. We're going to walk to the paleontological future of dinosaur colour research. The current picture is substantial, but incomplete. Multiple research directions are actively developing that will extend our understanding across the coming decades. The most obvious ongoing direction is the analysis of additional specimens. Every year, new dinosaur specimens are recovered from various fossil sites around the world. Some of these specimens preserve enough soft tissue for potential melanosome analysis. As new specimens accumulate, additional colour reconstructions become possible. The specific pace of new colour reconstructions has been substantial across the past 15 years. Sinosauropteryx in 2010, Anchiornis in 2010, Microraptor in 2012, Confuciusornis across the middle 2010s, Psittacosaurus in 2016, Borealopelta in 2017, Diplodocus in 2025. Additional species reconstructions are published every year or two. The pace of publication suggests that dozens more species will have their colours reconstructed across the coming decades. The most exciting new direction is the extension of the technique beyond the small feathered theropods. The traditional melanosome analysis has focused primarily on feathered specimens, but recent work has extended the technique to non-feathered specimens like Borealopelta and Psittacosaurus, and now to the great sauropods with the Diplodocus work. The specific extension to different dinosaur groups opens up the possibility of eventually reconstructing colours for species from many different lineages. The specific ambition of the field is to eventually reconstruct colours for at least one species in every major dinosaur group. Sauropods have been added to the reconstructed list. Ceratopsians have been added. Nodosaurs have been added. Small feathered theropods are extensively represented. The remaining major groups include the great tyrannosaurs, the hadrosaurs, the ankylosaurs proper, the stegosaurs, the ornithomimids, and various other groups. The specific extension to each of these groups is a research target for the coming years. Some of these extensions may be more difficult than others. The great tyrannosaurs, like Tyrannosaurus rex, have not yet produced specimens with adequate soft tissue preservation for melanosome analysis. This may change as new specimens are recovered, but it may also turn out that the specific preservation needed for T-Rex colour reconstruction is very difficult to find. The most famous dinosaur may remain colour unknown for some time. The hadrosaurs are a bit more promising. Some hadrosaur specimens preserve skin fragments with visible scale texture. Whether the specific preservation includes melanosome evidence is not yet fully documented, but the possibility exists. Hadrosaur colour reconstruction is a likely medium-term research target. The stegosaurs and ankylosaurs are similarly promising. The dinosaur groups with substantial skin preservation potential include several that have not yet had colour reconstructions. Ongoing analysis of existing specimens and future recovery of additional specimens will likely produce colour reconstructions for at least some species in these groups. Take a deep breath. The specific pace of expansion has been steady, and there is no reason to expect it to slow. Additional species reconstructions will accumulate. The overall picture of dinosaur coloration will become progressively more complete. There are also technical developments underway that will extend the analytical capabilities of the technique. New microscopy methods are being developed that can detect additional cellular structures in fossil tissue. New chemical analysis techniques are being developed that can potentially detect residues of non-melanosome pigments. New statistical methods are being developed that can extract more information from limited melanosome samples. Some of these technical developments may eventually allow detection of ultraviolet coloration components. Some may allow partial detection of carotenoid coloration. Some may allow better analysis of species that currently produce ambiguous results. The specific timeline for these technical developments is uncertain, but the general direction of methodological improvement is clear. The field will develop more sophisticated techniques across the coming decades, and these techniques will extend what can be reconstructed from fossil evidence. There is also increasing attention to specific ecological interpretation of the reconstructed colours. Current reconstructions typically identify specific colours and general functions like countershading or display. Future research may develop more sophisticated ecological interpretations that connect specific colour patterns to specific ecological contexts. The specific reconstructed patterns of species like Anchiornis and Microraptor may eventually be understood in more detail as evolutionary adaptations to specific ecological pressures. Which specific predators drove specific countershading patterns? Which specific mating strategies drove specific display features? Which specific habitat structures shape specific pattern variations? All of these questions are actively being explored. The whole field is one of the most active areas of modern paleontological research. New discoveries, new techniques, new interpretations, new specimens, new species reconstructed, new ecological interpretations. The pace of publication is substantial and shows no sign of slowing. Stay with this. Hold this gently. The paleontological future of dinosaur colour reconstruction is bright. What we can currently see is beautiful. What we will be able to see in the coming decades will be substantially more beautiful. We look forward to this future. We honour the current state of the field. We're grateful for what has already been achieved. We move on. We move on. We honour this deep evolutionary history. We move on. We honour this. We move on. We honour the pattern. We move on. We move on. We move on. We move on. When you visit her, you can see the specific countershading pattern that the melanosome analysis reconstructed. Her back is dark. Her belly is pale. The transition zone between the two extends along her flanks. She looks, in her museum display, exactly the way she would have looked in life. We honour her. We move on. Modern lyrebirds are still, in some deep evolutionary sense, using the same visual display grammar that Confuciusornis used. Confuciusornis lived alongside the other Yixian animals in her ecosystem. She hunted small insects and small invertebrates. She competed with other small predator species for the same food resources. She was probably preyed upon by larger theropods, like the various small dromaeosaurs and troodontids in the ecosystem. She lived her species life across the natural span of her species' existence. She has been extinct for tens of millions of years. Her lineage did not survive into the modern bird radiation. She is one of the many early bird lineages that emerged in the Cretaceous, achieved substantial evolutionary success for some millions of years, and then went extinct without leaving descendants that made it to the modern era. The modern bird radiation traces back to different early bird lineages, particularly the modern bird lineage that emerged in the late Cretaceous and survived the KPG extinction. Confuciusornis was not on that specific lineage. She was a separate early bird experiment that did not persist. But her colours have been preserved, her fossils are abundant, her species is one of the most fully known early birds in the entire fossil record. She lives, in some quiet sense, in modern paleontological understanding, even though her lineage has been extinct for over 100 million years. We honour her. We move on. Modern iridescent birds show similar patterns. Common ravens are iridescent black. Common grackles show extraordinary rainbow iridescence. Peacocks display their spectacular iridescent tail patterns. Hummingbirds show intense structural coloration in their throat patches. All of these modern iridescent bird colors are produced by the same specific melanosome arrangements that Microraptor used 125 million years earlier. The evolutionary continuity is direct. The specific structural coloration mechanisms that produce iridescence in modern birds were present in non-avian dinosaurs at least by the early Cretaceous. Microraptor was iridescent using the same physical principles that make modern crows iridescent today. Settle into this. Watch her in your imagination. She's perched on a branch in the Yixian forest, her small feathered body catching the morning sunlight. Her 4 wings are folded against her body. Her long tail extends behind her, and her entire feathered surface is a deep iridescent black, shifting with blue and green highlights as she moves her head or ruffles her feathers. She launches from her branch into flight. Her 4 wings extend and catch the air. She glides across a small clearing, her iridescent body flashing in the sunlight as she moves. She lands in another tree, folds her wings, resumes her hunt for the small mammals and small lizards that make up her diet. She is beautiful. She was beautiful when she lived. Her ecosystem was full of iridescent movement wherever Microraptor were active. Her colors served specific functions. The overall dark tone provided camouflage in the dim forest understory where she hunted. The iridescence, however, was probably a display feature, used in social communication with other Microraptor. Modern iridescent birds use their structural coloration primarily for species recognition and mate selection, and Microraptor almost certainly used her iridescence for similar functions. The specific evolutionary origin of feathered iridescence is one of the most interesting questions in modern feather biology. Iridescence requires very specific melanosome arrangements. The evolutionary path from non-iridescent feathers to iridescent feathers requires substantial genetic and developmental changes. The fact that Microraptor was iridescent 125 million years ago tells us that these changes had already occurred in the Dromaeosaur lineage by the early Cretaceous, and that structural iridescence was probably widespread across small feathered theropods much earlier than we might have guessed. The iridescent color continuity from Microraptor to modern crows is one of the deepest and most beautiful evolutionary connections in the modern bird dinosaur understanding. The same structural coloration mechanisms have been continuous in the Praevian to bird lineage for at least 125 million years, probably much longer. We watch her for a long quiet moment. She hunts through the Yixian forest, her iridescent body flashing occasionally in shafts of morning sunlight that penetrate the canopy. She is, in some quiet way, one of the most beautiful small dinosaurs the fossil record has ever preserved for our modern reconstruction. The specific iridescence of Microraptor tells us something important about the sensory ecology of the Yixian ecosystem. If she was iridescent, then the specific visual environment in which she lived must have been one where iridescence was ecologically meaningful. Sunlight had to penetrate the forest canopy in sufficient amounts and in sufficient angles for the specific iridescent flashes to be visible to her fellow Microraptor. The specific spatial and temporal patterns of forest light had to be complex enough that iridescent signals carried meaningful information. This tells us something about the specific Yixian forest structure. Modern forests with iridescent bird species show similar features. The canopy is not uniformly closed. Specific gaps and openings allow specific patterns of direct sunlight to reach lower levels of the forest. The specific microenvironments of these light gaps are where iridescent displays are most effective. Iridescent species tend to concentrate their display behaviors in specific spatial locations, where the specific lighting supports the visual signals. Microraptor probably used the specific Yixian light gaps for her specific display behaviors. She probably had specific perching sites in specific locations where the specific light conditions maximize the visibility of her iridescence. She probably had specific display routines that involved moving into these specific light conditions at specific times of day. The whole spatial and temporal pattern of her social communication was probably tuned to the specific visual environment of her ecosystem. Her specific colors mattered, but they mattered in specific contexts, at specific times, in specific locations. The full picture of her visual biology is more complex than a simple color reconstruction can capture. We honor this complexity. We watch her continue her hunt. We move on. We move on. We are set to walk toward the dawn now. Our long walk through dinosaur color reconstruction has been substantial. We have honored the specific reconstructions, the analytical technique, the research community, the Yixian ecosystem, the bird continuity, the evolutionary origins, the wider ecosystem context. We have covered much of the current state of the field. The morning is deepening around us in the Yixian forest where we began our walk. Sinosauropteryx is still active, moving through the forest floor on her small hunts. Anchiornis has spent the morning on her branch and is now beginning to move to a new watching position. Microraptor has completed his morning glide and is resting in a tree crown. Confuciusornis is calling from a nearby conifer, her small dark body catching the morning light. The whole Yixian ecosystem is alive with the specific colours we have been reconstructing throughout tonight. Let this settle. Watch the ecosystem for a long quiet moment. The coloured dinosaurs are participating in their daily activities. The forest is filled with visual signals of various kinds. The specific colours we have reconstructed are being used, in real time in the deep past, for their specific ecological functions. Camouflage is working. Countershading is hiding animals from predators. Iridescence is being flashed in social communication. Pattern variation is helping individuals recognize each other within their species groups. Every specific colour is doing specific work. The morning continues to brighten. The mist that hung over the lake at dawn has now fully lifted. The Yixian is bright and clear. The specific colours are visible in the full morning light. We are going to lift our awareness up above the forest for one last aerial view. We drift up above the conifer canopy. We can see the wider Yixian landscape spread out below us. The lake basins with their scattered small islands, the surrounding hillsides covered in forest, the various river systems that connect the lakes and drain the region, the volcanic peaks in the distance that will occasionally produce the ashfalls that will preserve so many of these animals for our modern examination. We can see, from this height, the movement of various dinosaur species across the landscape, the small feathered theropods active in the forest floor and canopy, the larger species patrolling their territories, the pterosaurs gliding overhead on the morning thermals. The whole ecosystem is alive with movement, and the movement is coloured. Every animal is wearing her specific reconstructed or inferred colour pattern. Every movement is a movement of specific colour across the landscape. The whole visual world is a symphony of coordinated movement and specific patterning. Take a deep breath. This is the Yixian at its most beautiful. A morning in the early Cretaceous, 125 million years ago, when the ecosystem was fully functioning and every species was participating in her specific role, when the specific colours we can now partially reconstruct were being worn by the actual living animals, when the visual world of a mature, stable dinosaur ecosystem was at its full richness. We have honoured this ecosystem tonight. We have honoured the specific species whose colours have been reconstructed. We have honoured the wider community context in which those colours serve their ecological functions. We have honoured the scientific research that has recovered our current partial understanding. The whole walk has been a slow, patient exploration of one of the most exciting subfields of modern paleontology, and it has been, in some quiet sense, a walk through the specific visible surface of the deep past, a walk through what dinosaurs actually looked like when they were living, breathing, coloured animals participating in their specific ecosystems. We drift back down through the canopy. We return to the level of the small feathered theropods. We are with Sinosauropteryx again, watching her from a short distance as she continues her morning activities. She's beautiful. Her back is ginger orange. Her belly is cream. Her tail is banded. She moves through the forest floor with the small, quick movements of a fast little predator. She catches an insect. She eats it. She continues her hunt. She does not know she has been observed. She does not know that her specific colors have been reconstructed by human science 125 million years after her death. She does not know that she is one of the most famous colored dinosaurs in the entire modern paleontological literature. She knows only her morning, her hunt, her small, careful life in the Yixian forest. We honor her for what she is, a real animal in a real ecosystem, wearing real specific colors that natural selection shaped into her lineage across millions of years of evolution. We are about to leave her now. The Yixian morning continues around her. She will spend her day hunting through the forest, resting through the heat of midday, hunting again in the late afternoon, sleeping in her chosen safe spot when night falls. She will continue this pattern for the natural span of her species' life. Her lineage did not survive the KP extinction. The specific compsognathid theropods went extinct at some point in the Cretaceous before the impact. No modern descendants exist. Her species is completely gone. But her fossilized remains preserved her specific colors. Human science recovered them. And now, in your imagination tonight, she is walking through the Yixian morning wearing her ginger and cream pattern, doing exactly what she did 125 million years ago when she was alive. That is beautiful. That is the specific gift that dinosaur color reconstruction has given us. We lift away from the Yixian, we drift back across 125 million years of deep time. We return, slowly, to your modern room, your modern bed, your modern night. We have walked through much of the dinosaur color story tonight. We have honored the specific reconstructions, Sinosauropteryx's ginger and cream body and banded tail, Anchiornis's rusty crest and pied wings, Microraptor's iridescent black feathers, Confuciusornis's pied plumage, Borealopelta's countershaded armor, Psittacosaurus's patterned flanks, Diplodocus's speckled sauropod skin. We have honored the specific technique, melanosome analysis, developed by Jacob Winter and collaborators at Yale and Bristol starting in the late 2000s, extended by multiple research teams across the following 15 years. We have honored the specific limits. Only a small percentage of dinosaur species will ever have their colors reconstructed. Many color mechanisms cannot be detected by current techniques. Individual variation and age-related variation are largely undocumented. Ultraviolet coloration is largely invisible to us. Carotenoid coloration is completely lost. We have honored the deeper patterns. Countershading was probably universal across dinosaurs. Display coloration was probably widespread. The specific evolutionary origin of dinosaur color mechanisms traces back through the pre-dinosaur vertebrate lineage. We have honored the continuity. Modern birds carry forward the specific color mechanisms that dinosaurs developed. Every modern bird you see uses color technology that traces back through the dinosaur lineage. The whole picture we have walked through is one of the most exciting recent developments in dinosaur paleontology. The specific colors of specific dinosaurs are being recovered from the fossil record for the first time in the history of the field. The visible surface of the deep past is becoming visible again through careful patient laboratory analysis of exceptionally preserved specimens. There is still much that we do not know. Most dinosaur species will remain color unknown. Many color mechanisms are invisible to current techniques. The specific ecological interpretation of dinosaur color patterns is often speculative. The paleontological research on dinosaur color is ongoing. Additional specimens will be analyzed. Additional techniques will be developed. Additional interpretations will be published. Our picture of dinosaur color will continue to develop across the coming decades. We hold the current picture lightly. We honor it gently. We are grateful to live in a century when so much of it can be reconstructed at all. Let your breath slow. Let your awareness rest gently on the entire story we have walked through tonight. The specific reconstructions, the analytical technique, the research community, the Yixian ecosystem, the bird continuity, the evolutionary origins, the wider ecosystem context, the Cretaceous night that now enfolds the sleeping-coloured dinosaurs, all of it in a single, long, slow walk together. This is one of the deepest satisfactions this channel can offer. Not just the honouring of dinosaurs as biological entities, but the honouring of their specific visible surface, what they actually looked like, what their specific colours were, how their species evolved to wear specific patterns for specific ecological reasons. Sinosauropteryx in her ginger and cream-banded body, Anchiornis in her rusty crest and pied wings, Microraptor in her iridescent black, Confuciusornis in her pied plumage, Borealopelta in her countershaded armour, Psittacosaurus in her patterned flanks, Diplodocus in her speckled skin, all of them tonight in your imagination, alive again in their specific colours that natural selection shaped into their lineages across millions of years of evolution. Let your breath slow. Let your body settle deeper into whatever supports you. Let the small last edges of your day go. The coloured dinosaurs are still in your imagination, wearing their specific patterns, participating in their specific ecosystems, doing what their specific colours evolved to help them do. Camouflage against predators, display for potential mates, species recognition among their fellow species members, individual identity within their social groups. They will be there, in your imagination, whenever you wish to return to them. The dinosaur colour story is paused in your mind. It is, in some quiet way, not entirely over. For tonight, though, we have walked enough. The specific colours of specific dinosaurs are still visible in your imagination. The specific ecosystems in which they lived are still functioning. The specific research communities that have recovered their colours are still working to expand our understanding. The whole story is still developing. We are, in some deep evolutionary sense, part of the story that follows. The specific colour mechanisms that dinosaurs developed have been preserved and elaborated by their modern bird descendants. Every modern bird colour you can imagine traces back through the intricate evolutionary history of dinosaur coloration. When you observe a modern bird tomorrow, in your modern morning, you will be observing an animal whose specific colours trace back through millions of years of dinosaur evolution. You will be observing the visible continuation of the dinosaur colour story. The dinosaur colours did not end with the KP extinction. They continue in every modern bird you see. The whole visual world of birds is in some quiet sense the ongoing story of dinosaur coloration. We are going to walk one final long quiet stretch before the close. We have honoured much of the dinosaur colour story tonight. There is one more theme worth walking through. What it means, in the larger sense, to recover the specific colours of extinct animals from fossil evidence. The recovery of specific dinosaur colours is one of the most quietly extraordinary achievements in modern science. Consider what has been accomplished. Specific animals died 125 million years ago. Their bodies fell into specific fossil-preserving environments. Their specific tissues were preserved with microscopic detail across the intervening geological time. Human scientists eventually excavated the specimens, developed analytical techniques capable of interpreting the specific preserved structures, and reconstructed the specific colours that the specific animals wore during their specific lives. The chain of preservation and recovery is remarkable. Each step required specific conditions to be right. The specific depositional environment, the specific taphonomic history, the specific fossilization chemistry, the specific human excavation, the specific analytical technique. All of these had to align for us to eventually see the specific colours. Most animal species that have ever lived on this planet have not left any fossil record at all. Their bodies decomposed without preservation. Their specific colours are completely and permanently lost to us. The vast majority of the colour history of vertebrate evolution is invisible. The specific handful of dinosaurs whose colours we can reconstruct are therefore precious. They are the exceptions who happen to fall into the right depositional environments at the right times, whose specific bodies happen to preserve enough microscopic detail, whose specific specimens happen to be excavated by researchers who happen to have the right analytical techniques. Each specific color reconstruction is, in some quiet way, a small miracle of paleontological preservation and recovery. Settle for a moment. Hold this gently. When you think about Sinosauropteryx's ginger and cream body, you're thinking about a specific real animal whose specific colors are now known to human science 125 million years after her death. This is one of the most remarkable achievements in the entire history of paleontology. The specific individual Sinosauropteryx who was analyzed was one specific individual of her species. She lived her natural life. She died. Her body was preserved. Her fossilized remains were eventually recovered by Chinese paleontologists. Her specific melanosome patterns were eventually analyzed by international research teams. Her specific colors were eventually reconstructed and published in the scientific literature. Her specific individual life is now recovered in ways that most individual lives, of most animal species, of most geological periods, will never be recovered. She's one of the small handful of extinct individuals whose specific visible surface is now known to human science. This is a kind of survival that goes beyond the biological. Her lineage went extinct long ago. Her species produced no direct descendants that survived to the modern era. In biological terms, she is gone, and her family is gone. But in scientific terms, her specific individual body left evidence sufficient for her specific colors to be recovered. She has, in some quiet sense, a kind of paleontological afterlife in modern scientific understanding. The same is true for every specific dinosaur whose colors have been reconstructed. Anchiornis has her paleontological afterlife. Microraptor has hers. Confuciusornis has hers. Borealopelta has hers. Psittacosaurus has hers. The specific Diplodocus individual whose skin was analyzed has hers. Each specific specimen has, in some quiet sense, achieved a form of continuation through the recovery of her specific colors. Breathe slow. There is something quietly moving about this. The animals themselves cannot know that their colors have been recovered. They died long before human science existed. They had no way of knowing that their specific individual bodies would eventually contribute to human paleontological understanding 125 million years later. But their specific individual patterns are now known. Their specific colors are now honored. Their specific individual existence has been recognized by human science and preserved in the scientific literature, and depicted in modern paleo art and discussed in modern documentaries. We are grateful to be able to do this. We are grateful to be alive during the specific historical moment when dinosaur color reconstruction has become possible. We are grateful to the specific researchers who have developed the techniques and analyzed the specimens and published the reconstructions. We are grateful, in some deep sense, to the specific animals themselves for leaving the evidence that made all of this possible. Take a deep breath. Let this settle gently. The dinosaurs we have honored tonight are 125 million years dead, but their specific colors are alive in your imagination. Their specific patterns are visible in the mental images you've been building throughout this walk. They are, in some quiet sense, walking again in your mind, wearing their specific reconstructed colors, doing what their specific colors evolved to help them do. This is one of the specific satisfactions this channel can offer. Not just information about dinosaurs, not just facts, but actual imagined presence of specific extinct animals in their specific colors, in your specific imagination, doing what they specifically did during their specific individual lives. The reconstruction is imperfect. We hold it lightly. But it is real to the specific extent that the melanosome analysis has enabled. The specific animals really wore the specific colors. We really can see them now, in mental images grounded in specific fossil evidence. We honor this. We honor them. The Yixian night continues around the sleeping colored dinosaurs. Sinosauropteryx is in her sheltered hollow. Anchiornis is on her canopy branch. Microraptor is in her tree crown roost. Confuciusornis is on her lower branch. All of them are sleeping in the specific colours we have honoured tonight. They will wake in the morning. They will spend their days in their specific ecosystems, doing their specific activities in their specific colours. They will continue doing this for as long as your imagination continues to hold them. Sleep well tonight, traveller. The coloured dinosaurs are sleeping too, all of us, together, in the deep continuous rest of the vertebrate world. There is one more small quiet thought to hold before we close. The specific colours we have recovered are the colours of specific individuals, but they represent in some sense entire species. When we honour Sinosauropteryx as ginger and cream, we are honouring not just the specific individual whose fossil was analysed, but the entire species she represents. Her specific individual pattern probably reflected some individual variation, but the general species pattern is what her specific individual body preserved. This is one of the deep satisfactions of specific paleontological reconstruction. Individual specimens carry the general species story. Individual bodies preserve the general species identity. Individual colours document the general species patterns. Every individual specimen is precious. Every individual body preserved. Every individual colour recovered. Together they build our specific picture of dinosaur species and their specific visible surfaces. The specific individuals become the general species representatives, and the general species become part of our modern understanding. The whole process is beautiful. Individual by individual, species by species, reconstruction by reconstruction. The picture develops over years and decades, and what emerges is our specific modern understanding of dinosaur coloration, one small piece at a time. We honour the individuals, we honour the species, we honour the process itself. Let your breath slow one final time. Let your body settle into whatever supports you tonight. Let the specific coloured dinosaurs walk one last time through your imagination, in their specific reconstructed patterns, moving through their specific Cretaceous environments, doing what their specific evolution shaped them to do. Sinosauropteryx moving through the Yixian mist with her banded tail flicking behind her. Anchiornis on her canopy branch with her rusty crest catching the morning light. Microraptor gliding between the trees with her iridescent black flashing in the sunbeams. Confuciusornis calling from her lower branch with her pied wings folded neatly at her sides. Borealopelta walking her Alberta shore with her countershaded armour providing quiet protection. Psittacosaurus browsing at the stream edge with her patterned flanks blending into the dappled forest shadow. Diplodocus in her Morrison herd with her speckled skin catching the golden Jurassic light. All of them together, all of them alive in your imagination, all of them wearing the specific colours that specific fossil evidence has allowed us to reconstruct. They will be there whenever you wish to return to them. The specific ginger of Sinosauropteryx, the specific rust of Anchiornis, the specific iridescent black of Microraptor, the specific pied pattern of Confuciusornis, the specific countershading of Borealopelta, the specific patterned flanks of Psittacosaurus, the specific speckled skin of Diplodocus. All of these are small, precious gifts of the modern paleontological century. We hold them gently as we settle for the night. Sleep well tonight, traveller. Good night.